If you dropped a glass and it shattered on the floor, would you ever expect it to jump back together again? Of course not. But here's the weird thing. According to the laws of physics, that's not actually impossible. Nothing in those laws says a broken glass can't reassemble itself. So why doesn't it ever happen? Why does time, and everything in our lives, only ever move forward? Every moment of your life sits on a current you can't escape, a one-way river that flows from the past into the future. You wake up, you grow older, ice melts into water, and smoke drifts away. Everything changes in one direction, and never the other. This flow is so obvious that we almost never question it. But what if the direction of time isn't built into the universe at all? What if it's just an illusion, a trick of probability, born from chaos and heat? Think about it. The world around us is obsessed with the idea of going back. Science fiction has dreamed of time travel for decades. We write stories where people undo mistakes, visit their younger selves, or rewrite history. But in real life, no one has ever managed to move even 1 second backward in time. If you film something in reverse, a shattered glass magically reassembling, smoke collapsing back into a candle, or ashes turning into wood, your brain instantly knows it's fake. It feels wrong. Here's what puzzles scientists. At the smallest scales, the math that describes reality doesn't care about direction. If you could reverse the motion of every particle in a broken glass, they could, in theory, retrace their paths and rebuild that glass perfectly. The equations allow it. The universe just never does it. So what's stopping it? Why is the past locked while the future remains open? What makes time, a thing we can't see or touch, always move one way, never two? To start answering that, imagine something simpler. Picture a cup of coffee sitting on a table. You pour in a splash of cream and watch it swirl, the white and brown mix, twisting and curling together until they're inseparable. Now imagine the process in reverse. The cream unmixing itself, curling back into a pure white pool, while the coffee turns dark again. You know that will never happen. You could wait the entire age of the universe, and it wouldn't occur once. This is what physicists call irreversibility. It's everywhere. In the melting of ice, the rusting of metal, the cooling of hot tea. Each of these processes moves toward a state of more disorder, never less. And the word scientists use for that disorder is entropy. Entropy is like a cosmic counter that measures how many ways things can be arranged while still looking the same overall. For example, there are countless ways for the molecules in your room to spread out evenly in the air, but only a few ways for them all to bunch up in one corner. That's why you never see all the air leave a room and pile up by the ceiling. There's nothing physically stopping it. It's just so incredibly unlikely that it might as well be impossible. So when you pour cream into coffee, entropy increases because there are far more mixed states than unmixed ones. The cream spreads out, not because the laws of nature tell it to, but because that's simply the most probable outcome. The universe doesn't forbid order, it just doesn't favor it. And that, quietly, is what gives us the arrow of time. It's not the equations that choose direction. It's probability. Every second that passes, the universe slips into one of the countless states that are more disordered than before. And because there are vastly more of those states than ordered ones, it's almost guaranteed that time will keep moving forward, toward more entropy. You might not notice it moment to moment, but entropy is rising all around you. It's in your cooling cup of tea, the fading warmth of sunlight after sunset, even in your heartbeat, which burns chemical energy into waste heat. Every heartbeat, every breath, every movement leaves the universe a little more disordered than before. Time's arrow is written into everything, not as a rule, but as a pattern of overwhelming likelihood. And yet, something about that seems unfair. Why does it only go one way? Why doesn't the universe start from chaos and gain order instead of losing it? To answer that, we have to step back about 13.8 billion years. When the universe began with the Big Bang, it was hot, dense, and incredibly smooth, meaning, paradoxically, low in entropy. It was a state of remarkable order, a sea of energy so uniform it would eventually give birth to everything we see today. That initial smoothness, that strange, low entropy starting point, is what allows all of history to unfold. If the universe had begun already disordered, there'd be no room for entropy to grow. No arrow of time. No before or after. In a sense, the forward flow of time is the universe remembering where it came from. An echo of that first ordered moment, still playing out billions of years later as everything slowly slides toward chaos. Here's the paradox. The laws of physics don't actually care about direction. They work perfectly well in reverse. A falling apple or a shattering glass could run backward in the equations, and the math would still make sense. But the conditions of the universe, that improbably ordered beginning, broke the symmetry. From that moment on, everything started tumbling down the hill of probability, and we've been rolling ever since. Once you start seeing time as a kind of slope, a gradient of increasing entropy, you begin to notice its fingerprints everywhere. Why do we age? Why do memories form in only one direction? Why does cause always precede effect? It all ties back to that slope. Your body runs on chemical reactions that turn food into energy and heat. That heat diffuses into the environment and can't be perfectly recovered. Entropy wins again. Even thought itself follows the same rule. When you think, neurons fire and dissipate energy. Your memories are physical traces, irreversible imprints left by those tiny chemical events. You can remember the past because it left evidence behind. A footprint, a photograph, a pattern of neurons. But the future leaves no trace yet. Entropy guarantees that we can only build memories one way, downstream. Light follows the same current. When you switch on a lamp, photons rush outward and scatter, never to gather again. Every beam that bounces off your skin or the walls becomes a record of now, proof that this moment happened. You are literally radiating your past into the universe at the speed of light. Entropy isn't just a number. It's the stage where time performs. And the more we study it, the stranger it gets. Because while entropy always increases, it does so unevenly. Inside your refrigerator, entropy decreases locally to keep things cool, but only by dumping more heat, and therefore entropy, into the room. The universe allows small pockets of order, your body, a planet, a city, but only by making the surroundings more chaotic. Life itself is a rebellion against entropy, but one that ultimately serves its master, speeding the overall disorder along. It's almost poetic. To exist at all, we must constantly consume order and produce chaos. Through that exchange, we experience time. It's not our enemy. It's the price of being alive. If you could somehow reverse every atom, every photon, every motion in the universe, everything would indeed run backward. Your coffee would unmix. Your heartbeat would unbeat. Your mind would forget. But you would never feel it, because consciousness itself depends on the forward cascade of cause and effect. The arrow of time isn't just out there, it's inside you, written into every cell, every thought, every heartbeat. Even if you could step into a reversed world, you wouldn't notice. Your memories would unravel in sync. You'd still feel time moving forward, even as everything else rewound. It's not that time flows forward, it's that we do, carried along its gradient. And here's the humbling part. One day, that gradient will flatten. When the universe reaches maximum entropy, a state of perfect uniformity and cold, time itself may lose meaning. There will be no more change to measure its passage. No past, no future. Just stillness. But until that distant day, the arrow continues. Every heartbeat, every sunrise, every falling leaf is the universe sliding forward, one irreversible moment at a time. We, fragile and fleeting, get to ride that current for a little while and call it life. So, why does time move forward and never back? Because it's not just a rule. It's the unfolding of improbability. The universe moves from the rare to the common, from the smooth to the messy, from that low entropy beginning toward the vast disorder ahead. And within that one-way flow, everything we know, memory, change, and life itself, finds its rhythm. On a quiet morning, you pour a dash of cream into your cup of black coffee. White tendrils of cream curl and billow into the dark liquid, making delicate swirls. For a minute, there is a beautiful marbling of white and black, patterns that shift and dance. But soon the mixture turns a uniform light brown. The cream and coffee become one, blended completely. No matter how long you wait, you'll never see the cream separate back out into neat white ribbons. That once distinct swirl is gone for good. Now consider the task of cleaning a messy room. Putting each toy block and doll back in its exact place takes far more effort than the mess took to create. Left alone, the room will not organize itself. If anything, it will gather dust and grow even messier. There are so many ways for the toys to lie scattered, and only a few ways to arrange them neatly. It's easy to stumble into a mess, but exceedingly unlikely that everything will magically return to order on its own. Without someone deliberately imposing tidiness, the room would stay in disarray indefinitely. This simple fact hints at a profound truth about our universe. Messy states vastly outnumber tidy ones. There are countless possible configurations of objects that look disordered, and relatively few that look ordered. If each configuration is equally possible, the odds are overwhelming that things will end up jumbled rather than neat. It's not that some mysterious force is actively causing chaos. It's just that disorder is far more probable. An orderly arrangement is a special, uncommon case amid a sea of randomness. Scientists use a concept called entropy to talk about this tendency toward disorder. Entropy is essentially a measure of how disorganized or random a system is. Low entropy means a state of order, like a tidy room where everything is in place. High entropy means disorder, like toys strewn everywhere. One of the key insights of physics is that in an isolated system, entropy tends to increase over time. In plain language, things naturally drift from order toward disorder as time moves forward. Even when we try to reverse a mess, we can't escape entropy's influence. Suppose you, or a helpful parent, clean up that playroom, carefully putting each toy back in its spot. Locally, the room's entropy has gone down. It's more orderly. But that effort wasn't free. You used up energy, your body warmed slightly, you breathed harder. The energy expended generates heat and disorder elsewhere, in the air of the room and within your body. Overall, the total entropy of the broader system, you plus the room plus the environment, still increases. Tidying one spot simply shuffles the disorder somewhere else. This idea is captured in the second law of thermodynamics, which says that the entropy of a closed system will not decrease. In all of human experience, we've never seen this law broken. It's one way to state time's arrow. As time marches on, total entropy grows. To build more intuition, imagine tossing a jigsaw puzzle into the air and letting the pieces scatter on the floor. They will land in a random heap. Perhaps a few pieces might coincidentally interlock, but the full picture will not magically assemble itself. The chance of them falling perfectly into a completed image is effectively zero. Similarly, picture a deck of playing cards flung onto a table. If by some miracle the cards landed perfectly sorted by value and suit, you'd be astonished. It's practically impossible. By comparison, any random scatter of cards looks messy, and there are astronomically many more messy arrangements than ordered ones. That's why a random shuffle yields a haphazard deck, not a neatly organized one. Whether we're talking about puzzle pieces, cards, or molecules of air in a room, there are far more ways to be disordered than ordered. If nothing special intervenes, a system will naturally wander into one of the numerous disorderly states, instead of staying in a rare orderly one. Entropy gives us a useful handle on the arrow of time. It increases. It counts how many ways things can be arranged, and as the count of messy arrangements overwhelms the count of neat ones, the future is statistically likely to be more disordered than the past. That's why spilled milk doesn't unspill, why your coffee cools down rather than heating up on its own, and why rooms get untidy when we ignore them. Even the universe as a whole tends toward higher entropy, a kind of gradual mixing and dispersal of energy. This isn't because nature prefers mess in any emotional sense. It's simply a matter of sheer numbers. Time's arrow, in a very real way, is the arrow of increasing entropy. Even though we often speak of entropy increasing as if it were a strict rule, there is actually no cosmic commandment forcing the universe to become more disordered. In truth, time's arrow emerges from simple chance playing out among huge numbers of particles. The laws of physics at the microscopic level don't actually prefer things one way or the other. An atom or molecule following Newton's equations, or quantum rules, can move forward or backward in time without breaking any fundamental law. If you could watch two tiny particles collide and then reverse the film, the motion would still make perfect physical sense. Nothing about that isolated collision points to an inherent direction for time. Yet when you have trillions upon trillions of such particles together, the story changes. The reason is sheer probability. While physics doesn't forbid an egg from unbreaking or coffee from unmixing, the odds of all the microscopic constituents coordinating just right to make that happen are astronomically small. It's a bit like shaking a million coins in a box. There's no law saying they can't all land heads up, but you would likely never see it happen in a million lifetimes. By pure chance, nearly every outcome will be a jumbled mix of heads and tails. In the same way, with countless molecules in a splash of spilled milk, nothing forces them to stay spilled except the overwhelming number of messy configurations compared to the one perfectly unspilled arrangement. Imagine the air in your living room. It's made of an enormous number of molecules bouncing around. There's no rule that forbids all those air molecules from randomly crowding into one corner of the room for a moment, leaving a vacuum in the rest of the space. In principle, it could happen by a fluke, since each molecule is just moving on its own and could, by chance, wander in the same direction as many others. But the probability of that occurring is so absurdly low that you could wait for billions upon billions of years and never witness it. Instead, what you experience is air spreading out evenly to fill the room, always. From our human perspective, that even spread feels like a law of nature. But underneath, it's really just the overwhelmingly likely outcome. This is the crux of the second law's statistical nature. It isn't that entropy cannot ever decrease. It's just that it almost certainly won't when huge numbers of particles are involved. In a microscopic, carefully controlled system with only a few components, you might occasionally catch a tiny decrease in entropy, a random fluctuation where, say, a handful of particles happen to gather into a more orderly arrangement for a split second. But in any everyday chunk of the world, those rare fluctuations are drowned out by a vast number of opposite, disordering events happening at the same time. Order can momentarily bloom in a small nook, but always at the expense of greater disorder elsewhere, and such brief blooms vanish quickly. The dice of chance keep rolling, and with so many dice in play, the odds overwhelmingly favour entropy rising overall. A 19th century physicist named Ludwig Boltzmann was the first to truly grasp this. At a time when many of his peers were baffled by the arrow of time, Boltzmann looked to statistics for the answer. He realized that the arrow is not mandated by any new force of nature, but by probabilities piling up as the number of particles grows. It was a bold idea in his era, one that many of his contemporaries found hard to accept. But Boltzmann's insight was correct. Boltzmann painted a picture of countless atoms moving chaotically, where the most likely collective behavior is one of increasing mess. In his view, the second law of thermodynamics was a law of statistics. The universe isn't actively destroying order. It's just exploring the vast terrain of disorder far more often than the tiny isle of order, simply because that chaotic terrain is immensely larger. This perspective explains why we never actually see time reverse in everyday life. Theoretically, if all the molecules in a broken egg just happen to jostle in exactly the right way at the same moment, the egg could reassemble itself. Physics doesn't forbid it outright. But the chance of that happening is so close to zero that in practice it's never observed. Time's arrow is, effectively, a reflection of overwhelming odds. It's chance, not command, that makes eggs scramble and stay scrambled, that makes cream mix into coffee and never unmix. With this understanding, we see that the forward flow of time is deeply rooted in the collective behavior of matter and energy. Time's arrow is a kind of statistical pressure, a one-way momentum born from the combined motions of uncountable particles. Still, one question lingers. If disorder is so much more likely, why was the universe ever orderly to begin with? After all, to have a direction to go, we must have started somewhere special. What set up the dominoes for entropy to begin its rise? To explore that mystery, we must travel back to the very start of time as we know it, to the early universe's incredibly low entropy beginning. Picture the universe in its infancy. A few moments after the Big Bang, everything is hot, dense, and astonishingly uniform. Instead of a sky full of stars or galaxies, there is a smooth, glowing fog of energy and matter stretching out in all directions. It's almost perfectly even, one vast cosmic cloud without any clusters or clumps. This early universe is simple in its structure. No galaxies, no stars, certainly no black holes or planets. Just a bright, almost featureless fireball, the same everywhere you look. This uniform beginning was something truly special. By most measures, it was an extremely low entropy state, and state of extraordinary order on a cosmic scale. That might sound surprising, since hot and dense doesn't sound orderly to us. But the key is how evenly everything was spread. Gravity, which later would pull matter into clumps and structures, hadn't had time to do so yet. There were no dense pockets of mass collapsing in on themselves. Compared to what could have been, say, a universe filled with scattered black holes or lumps of matter, this smooth blend of particles was remarkably organized. Physicists refer to the assumption that the universe started out in such an ordered condition as the past hypothesis. It's essentially the idea that the past, specifically the universe's beginning, had an incredibly low entropy, far lower than the entropy we see today. This low entropy beginning is the very reason time has a direction at all. It's as if the universe was born with a huge arrow pointing toward the future, set by this pristine order that would only degrade as time went on. From that first moment onward, entropy had only one way to go: up. Time's arrow was launched by the simple fact that the cosmos began in an almost unbelievably neat arrangement, and that has made all the difference. For perspective, out of all the countless ways matter and energy could have been arranged at the start, our universe happened to begin in one of the most orderly configurations imaginable. It's as if you shuffled a deck of cards and it came out perfectly sorted. Yet even that analogy doesn't fully capture how unlikely our universe's starting order was. In effect, the odds of such a low entropy birth were so close to zero as to be essentially nil. Yet for some reason it happened. Why the universe started off this way remains one of the deepest questions in physics. Perhaps some process during the Big Bang, like a brief burst of cosmic inflation, set the initial conditions just so, smoothing out the young universe. Or maybe our universe is one of many, and we happen to inhabit one that got lucky and began in a low entropy state. We don't yet know the full answer, but given this strange, orderly kickoff, everything that followed has been part of the natural drive toward higher entropy. Time's arrow was, in a sense, wound up at the beginning like a tightly coiled spring, and ever since, it's been unwinding. As the eons passed, that early uniform fireball expanded and cooled. Tiny variations, just the slightest wrinkles in the smoothness, gradually grew under the influence of gravity. Matter clumped into the first stars and galaxies. When the first stars ignited, they began the long process of fusing light elements into heavier ones and radiating energy into space, a grand increase in entropy on a stellar scale. Over billions of years, stars have burned through their fuel, galaxies have collided and scattered, and entropy has climbed and climbed. Every brilliant sunrise, every distant supernova explosion, every drift of interstellar dust is a step along this one-way road from order toward disorder, set in motion by the cosmos's beginning. Even our own existence is tied into this arrow. The sun's warmth that makes life on Earth possible is generated by nuclear reactions that steadily increase entropy, turning hydrogen into helium and radiating energy into space. We live and breathe thanks to energy flowing from something hot, the sun, to something cold, the darkness of space. Yet another irreversible process rooted in the universe's initial conditions. From the tiniest scales of life to the largest scales of galaxies, we are all riders on this journey begun at time's first moments. With the arrow of time established at the dawn of the universe, we can now see it manifesting everywhere around us. From cosmic events to humble everyday moments, the push from past order to future disorder continues unceasingly. Let's step back from the grand cosmic scale and watch how this same irreversible flow unfolds in the familiar scenes of daily life, in the mixing of a cup of coffee, the weathering of a rock, or the cooling of a warm meal. These humble events are, at their heart, echoes of that great beginning, each one a small irreversible moment propelled by time's one-way march. On a quiet morning in your kitchen, you stir a spoonful of cream into a cup of dark coffee. Delicate white tendrils curl into the blackness, creating beautiful swirling patterns. For a short while, you can see intricate wisps of cream within the coffee. But as you watch, those wisps dissolve, and the mixture becomes a uniform soft brown. No matter how long you wait, you'll never witness the cream undoing itself and gathering back apart from the coffee. The moment of separation is gone, and the two fluids have become one. An hour later, the The coffee is thoroughly mixed, and cooler too, as heat escapes from the cup. The process cannot naturally reverse. The cream will not leap out of solution to return to the shape of a spoonful, and the coffee will not grow hot again on its own. Time, in this simple act, has moved irreversibly forward. Imagine, then, that you accidentally knock the coffee cup off the table. It falls to the floor and shatters into pieces. Porcelain fragments scatter across the tiles, and a splash of coffee fans out around them. In an instant, a perfectly whole cup is reduced to a mess of broken shards and a puddle of liquid. You could gather the pieces and perhaps glue the cup back together, but it would never be quite the same. Fine crack lines would trace where it broke. And if you simply walk away, those ceramic bits will remain scattered indefinitely. They certainly won't jump up on their own, reform into a cup, and pull the spilled coffee back inside. The breaking of the cup is final. It starkly divides the world into before, when the cup was intact, and after, when it lies in pieces. Even simple changes of state follow this one-way pattern. Take an ice cube out of the freezer and place it on the table. In a short while, it will melt into a small puddle of water. The liquid water may then slowly evaporate into the air, dispersing entirely. But you will never see the reverse happen naturally. Water vapor gathering and cooling to form a puddle, then reassembling itself into a solid cube of ice. Once the ice has melted, that particular shape and order is gone, unless we intervene by freezing the water again with external cooling. Outside in the yard, the same one-way story unfolds in slower motion. Consider an old iron gate left exposed to the elements. Years of air and rain gradually work on it, and a reddish-brown film of rust creeps over the metal. The once smooth iron surface becomes rough and flaky as it transforms into iron oxide. If you brush your hand against it, your fingers come away dusty orange. The gate's metal has oxidized. It's gone from a shiny, solid structure to a brittle, corroded one. It's impossible for that rust to turn itself back into fresh metal. Without deliberate effort, like sanding and repainting, the rusting will continue, nibbling away at the iron, but never reversing into new iron. The decay of the gate is a slow, irreversible crawling forward of time. Walk through a quiet forest, and you'll find more evidence of time's irreversibility. An autumn leaf, once green and full of life on a tree branch, lies on the ground, dried to a crisp brown. Over weeks and months, it crumbles into smaller bits and blends into the soil. The change only goes one direction. The tree will not take that dead leaf and restore it to living green. Nearby, a fallen log gradually decays as well. Its wood softens, moss creeps over it. Insects and fungi break it down from within. It will never undecay into a fresh log. In nature, everything moves from new to old, from whole to broken, from organized to dispersed, given enough time. If you've ever watched a film of these kinds of events played in reverse, you know how uncanny and mesmerizing it looks. Imagine seeing a film of coffee and cream, unmixing, the light brown cup of coffee separating itself back into black coffee and white cream. Or picture those shattered ceramic pieces on the floor suddenly sliding and hopping back together, reassembling into a cup while the spilled coffee jumps up into it. Played backward, rust on a gate magically gathers and disappears, leaving shiny metal behind. Fallen leaves leap from the ground back onto branches and turn green. We find such reverse sequences fascinating precisely because we never see them happen in reality. They are like tricks or magic illusions, violating the normal order of things. In the real world, we only see time run forward. In each of these moments, something has been lost or dispersed that cannot be spontaneously recovered. A pattern or structure, whether it's the distinct separation of cream and coffee, the intact form of a porcelain cup, the crystalline solidity of an ice cube, or the polished surface of fresh metal, has given way to disorder. These everyday changes all share a common theme. They go in one direction, aligned with time's arrow. Though the settings differ, the underlying trend is the same. Things become jumbled, spread out, or broken over time. The arrow of increasing entropy quietly guides each of these events, ensuring that each transformation is irreversible. All the irreversible changes we observe, mixing, breaking, melting, decaying, are really manifestations of the same underlying arrow of time. In each case, something organized turns into something more spread out or random. Heat disperses, structures fall apart, concentrated energy dissipates. This is the thermodynamic arrow of time, and it's universal. The details differ from one situation to another, but fundamentally, whether it's a melting ice cube or a rusting gate, they all march along time's one-way street toward greater entropy, disorder. Consider how heat behaves. If you pour yourself a steaming cup of tea and then forget about it, the tea will gradually cool down to room temperature. The heat energy from the tea flows out into the surrounding air, warming the air ever so slightly. You might even see faint wisps of steam wafting above the cup, disappearing as the warmth disperses. What never happens is the reverse. A cold cup of tea sitting out doesn't spontaneously draw heat from the air and become piping hot. We always see heat move from a warmer object to a cooler one until both reach the same temperature. This one-way flow of heat is a classic example of time's arrow in action. Essentially, it's entropy increasing, the tea's concentrated warmth spreading out into the room, becoming more diffuse and evenly distributed. The arrow also appears in chemical reactions. Light a candle, and its solid wax slowly burns into wisps of carbon dioxide and water vapor, and a bit of soot, releasing a gentle glow of light and warmth. Once the candle has melted and burned down, you're left with a puddle of wax and a charred wick. You will not see those gases and soot ever gather themselves back into a pristine candle. Likewise, if you burn a sheet of paper to ashes, you'll never witness the ash and smoke reassembling into unburned paper. Chemical changes tend to go one way under ordinary conditions. Fuel turns to exhaust. Food spoils rather than unspoils. Metal corrodes rather than uncorrodes. All of these processes obey the same tendency toward greater entropy, as useful energy is used up and spread around. Even mechanical processes line up with this arrow. Imagine a child spinning a toy top on the floor. At first it twirls quickly, humming with energy, but eventually it slows and wobbles, then falls over. Friction with the air and floor steals the top's organized motion, turning it into a tiny bit of dispersed heat. The top never spontaneously spins faster or stands itself back up once it has slowed. It only goes from lively motion to stillness, not the other way around. In a similar way, a rolling ball will come to a stop as its energy dissipates into the environment. We never see a motionless ball start rolling by, absorbing random heat energy from the air. All these energy transformations flow one way. More concentrated forms of energy, like organized motion, inevitably turn into more spread out forms, like gentle warmth dispersed through the surroundings. In short, all these arrows, thermal, chemical, mechanical, and so on, point in the same direction. They are aligned facets of one grand increase in entropy. This principle is enshrined in the second law of thermodynamics. In any closed system, total entropy will not decrease. That is why we consistently observe the same forward time direction in so many phenomena. If ever, by some fantastic chance, heat did flow from cold to hot by itself, or shattered glass pieces did neatly reassemble. It would mean a local decrease in entropy, essentially a brief reversal of time's arrow. But in the natural world, such events do not occur. Even life's processes follow this principle. An organism can grow and build order only by consuming energy and releasing waste, so overall, entropy still increases. Instead, every experience we have reinforces the same truth. Time moves forward, and things inevitably move from order to disorder. All the arrows of change we observe are ultimately facets of one single arrow, the arrow of time, defined by increasing entropy. From ancient days to the present, human beings have been quietly devising ways to track the passage of time. There is something profoundly reassuring about giving structure to the flow of hours and days, even though we know we cannot halt or reverse it. Long ago, people watched shadows shorten and lengthen with the sun, and noticed the cyclic return of seasons and stars. They learned to mark these repetitions: the morning sunrise, the full moon, the longest day of the year. In doing so, they created the first rudimentary calendars and time markers, tying human life to the steady rhythms of the cosmos. Early timekeepers were often simple and serene. Imagine a stone sundial in the courtyard of an ancient city. As the day unfolds, the sun's light casts a shadow of the dial's pointer onto a flat surface etched with hour markings. Slowly, silently, the shadow creeps along, a dark line inching forward in step with the sun's journey across the sky. By midday, the shadow is short. By late afternoon, it stretches long. No sound is made. Yet by the movement of that shadow, one can tell the time. When evening comes and the sun sets, the sundial's job is done for the day. An elegant, if temporary, record of time's advance. But time does not stop at night, and so other methods were born. In a quiet temple courtyard, a bronze bowl filled with water sits with a tiny hole near its base. A steady drip of water escapes, drop by drop. After a known interval, the bowl will empty, a water clock marking a span of time in the dark hours when the sun is absent. Such a device, known as a clepsydra, measures time by a gentle rhythmic loss of water. Drip by drip, the passing moments accumulate in a lower vessel. Monks or scholars might check the water level to gauge how many hours had gone by. In another device, an hourglass, fine sand streams from an upper chamber to a lower one in a graceful, silent flow. The heap of sand below grows grain by grain. When the top chamber is empty, a fixed amount of time has elapsed. Flip the glass, and the flow begins again, always in the same direction for each turn. These early clocks have no moving hands or gears, just the quiet movement of water or sand, obedient to gravity, giving a measure to the otherwise invisible march of time. As craftsmanship advanced, people built mechanical clocks that tick and tock. Picture a medieval clock tower in a small town. Behind its wooden clock face and iron gears, a heavy weight slowly descends, driving the mechanism. Each swing of a pendulum or turn of a gear produces a measured tick. A bell chimes softly to mark each hour. These clocks segment time into equal parts, their gears advancing with satisfying precision. Indoors, a pendulum clock might sit in a study, its brass pendulum swinging left and right in a steady rhythm like a heartbeat. Each swing forward is a tiny step into the future. Each quiet tock that follows counts a moment that has just passed and will not return. The room might be silent, save for that gentle tick-tock, a comforting reminder that time is steadily moving, second by second. Today, our timekeeping has become even more exacting. We wear wristwatches regulated by the vibrations of quartz crystals, and we build atomic clocks that count the oscillations of cesium atoms. These modern marvels can divide a single second into billions of tiny ticks with astonishing accuracy. Yet, at their core, they are simply more refined versions of an ancient idea, using a regular, repeating process to measure the ceaseless flow of time. Whether it's dripping water, flowing sand, a swinging pendulum, or the subtle humming of an atom, the goal is the same: to mark out equal moments from a flow that never pauses. Clocks and calendars have given us the ability to organize our lives, to know when we are in the stream of time. A calendar turns the continuous sweep of time into a pattern of days, months, and years. A clock turns the day into slices of hours and minutes. We take comfort in these structures, scheduling our world by them. But even as we set our watches or celebrate a new year, we understand on some level that time itself flows onward, indifferent to our measurements. The clock's hands circle around, but time itself never circles back. There is a gentle irony in our relationship with time. We measure it meticulously. We name each passing fragment, all while knowing we cannot reclaim a single moment once it's gone. Still, the practice of timekeeping is a kind of reverence, an ode to the present moment, even as it slips into the past. Each tick of a clock, each turn of a calendar page, is a quiet acknowledgement of time's arrow. It's our way of saying, "We see you passing," to the hours. The flow of time never turns back on itself, but by tracking it, we make the one-way journey a bit more familiar, a bit less mysterious. In the end, every clock and calendar is our companion on this voyage, gently ticking alongside us as we move forward through life. Time is often compared to a door that only opens one way, outward, from the past into the future. Once we pass through a moment, we cannot go back. We carry the memory of where we've been, but we cannot re-enter yesterday. In a sense, our memories are like footprints left on the path of time. We can look at them behind us, but we cannot retrace our steps to where they began. This one-way door of time is fundamental to everything we do and experience. You can sense this one-way flow in the realm of the mind. Think about memory. We remember the past, but we cannot remember the future. You recall what you ate for dinner last night, but you have no knowledge of dinners yet to come. Our minds are built to record moments after they happen, never before. We feel the arrow of time in the steady accumulation of experiences. Childhood turning into adulthood. Old photographs reminding us of days gone by. We cannot reverse our personal timeline any more than we can unring a bell. This psychological arrow of time means we perceive cause and effect in one order only. Cause comes first, effect later. We intuitively know that we can influence the future, but not the past. Our entire sense of learning, aging, and history depends on the fact that time moves irreversibly forward in our minds. The one-way door shows up in the physical world of light and sound as well. Strike a bell, and it emits a clear note that radiates outward. The sound waves travel through the air and gradually fade away. They don't gather themselves back to the bell. Similarly, when a firework explodes in the sky, flashes of light burst outward in all directions. We see the glow and hear the boom as the energy spreads into the night. We never observe the reverse, a diffuse flash of light suddenly contracting into a pinpoint and unexploding. Light itself follows an arrow. It typically travels outward from its source. We see starlight that has journeyed for years toward us, but we never see light somehow rushing backward into the stars. In every case, radiation spreads out as time moves on, never the other way around. Even the universe as a whole moves one way in time on the grandest scale. Astronomers observe that the cosmos is expanding. Galaxies are drifting apart. Space itself is stretching and cooling as the eons pass. In the distant past, everything was closer together. In the far future, it will likely be more diffuse and cold. This cosmological arrow of time points from a hot, dense early universe, with low entropy, as we've discussed, to an ever more spread out, high entropy state. The universe's evolution has a direction. It grows older, not younger, larger and emptier, not smaller, at least in the era we inhabit. Like a clock that never runs backward, the cosmos keeps unfolding forward into new and more dilute configurations. All these arrows, psychological, radiative, cosmological, align with the same thermodynamic arrow we've come to understand. They all point outward through time's one-way door. We find ourselves standing at that door, always stepping forward into the unknown territory of the next moment. We cannot turn around and walk back into yesterday. So instead we build narratives of memory and expectation to live with this irreversible flow. The stage is now set to explore these deeper aspects of time's arrow. In the journey ahead, we will delve into why our minds cling to the past, why light and causality radiate outward, and how the entire universe marches toward its future. The door of time only opens out, and as we move through it, more mysteries await us on the other side. All the different arrows of time we have explored, the remembering of the past, the chain of cause and effect, the one-way spreading of light and sound, the quiet dissipation of friction, and the cost of erasing information, are not isolated quirks. They are threads of one grand tapestry, all woven together by the same underlying principle. In each case, something goes from a state of order to a state of disorder. Energy spreads out, information is lost to heat, patterns become scrambled. We recognize this as the increase of entropy, the fundamental trend that gives time its direction. The reason a footprint, a cooling cup of tea, a fading memory, and a computing circuit all march forward is that, in each, a bit of the world's order is turning into disorder, irreversibly. Consider, for example, a simple mishap. You are holding a porcelain cup of tea, and it slips from your fingers. The cup falls and shatters on the floor. In that brief moment, all the arrows of time reveal themselves. Your memory of the cup exists up until the moment before it fell. Afterward, you can only recall the event, not foresee it. The cause, the slip, comes before the effect, the broken cup. The crash sends sound waves ringing through the air, spreading outward and never gathering back. The cup's orderly form is lost, its pieces scattered, its heat and sound dissipated into the room. You can sweep up the fragments and perhaps keep them, but you cannot reassemble the cup as it was. The event is irreversible. A humble kitchen accident encapsulates time's one-way flow in miniature. It is astonishing, in a way, that so many aspects of our experience, from the cosmic scale of starlight to the intimate workings of our minds, share the same arrow. A star shines, and its light travels outward, never to reconverge. A living creature is born, accumulates memories and wear, and eventually ages, never growing younger. Each process is different in detail, yet all obey the same temporal orientation. This unity tells us that time's arrow is something deeply built into the fabric of reality, not just a coincidental feature of one phenomenon or another. It arises from the conditions of our universe as a whole. Physicists believe that the key lies in the way the universe began. The story goes back to the very dawn of time, to the Big Bang and the state of the young cosmos. By all indications, the early universe was an extremely hot, dense, yet surprisingly ordered place. It had incredibly low entropy relative to what it could have been. That initial order is like a primed canvas on which the arrow of time could begin painting. As the universe expanded and cooled, entropy began to increase. Structures formed and then decayed. Concentrations of energy spread out. Over billions of years, stars have burned their fuel, galaxies have drifted and merged, and in pockets of the universe like our planet, life emerged and started doing its own complex dance under time's arrow. All of this unfolding drama has been a journey from an initially ordered state toward increasing disorder. And that journey continues even now, as the cosmos carries on evolving and dispersing energy. Why the universe started in such an ordered condition is a profound mystery. It is one of the great unanswered questions in physics. Some suggest that it might be a result of deep laws of cosmology or something special about the Big Bang, while others admit we simply don't yet know. But what we do know is that this low entropy beginning is the ultimate source of the arrows of time we experience. Because the universe began in a state of high order, there has been a direction for time to roll downhill, so to speak, ever since. Every cup of coffee cooling, every memory forming, and every star shining is participating in this grand, one-way evolution that started at the beginning of time. When we look at the world through this lens, we see time's arrow everywhere. It is in the cracks of ancient rocks and the light of distant galaxies, in the decay of old wood and the sparks in a computer chip. It connects the gentle fading of a day's light to the ticking of your thoughts and the warmth of a busy city at night. All are manifestations of the same cosmic progression. We, as thinking beings, ride this river of time along with everything else, carried from what was to what will be. Understanding that these arrows are really one can change how we view our everyday phenomena. The next time you watch ice melt in a glass, or see a trail of footprints on the beach, gradually washed away by the tide, you might recall that these humble events are playing out the very same principle that governs the aging of the stars and the expansion of the universe. There is a profound continuity in it. This is a reassurance that our small experiences of time's passage are connected to the grand story of the cosmos. As our journey through the arrows of time comes to a close, we find ourselves returned to a singular idea, that the flow of time is rooted in the tendency of the universe to move from order to disorder. Each arrow we followed pointed back to this common source. But this is not truly the end of the story. It opens up further wonder. Why should the universe have been so ordered at the start? What does it mean for the far future as entropy continues to rise? These questions beckon us onward, inviting us to look deeper into the nature of time itself. Some scientists have speculated about what the arrow of time might mean in the far future. If the universe continues to expand and entropy keeps increasing, a day may come, trillions upon trillions of years from now, when nearly all usable energy is spent. In this hypothetical far future state, often called heat death, everything would be spread thin and even, with no gradients to drive change. Time's arrow would effectively lose its power there, because there would be no more order left to unravel into disorder. No stars would shine, no life would stir, and no new memories would form, for there would be no free energy to fuel them. It is a distant and melancholy vision, the ultimate fulfillment of the second law's promise. And yet, that fate is almost unimaginably far off, and the cosmos has a great deal of story left to tell before then. For now, time's arrow remains vital and unyielding, propelling galaxies, life, and every ticking second of our experience forward. So, as we stand here, aware that we remember yesterday, but not tomorrow, warmed by the gentle irreversibility of all our actions, we can appreciate the subtle connections linking our lives to the stars above. The arrow of time, threading through memory, causality, and thermodynamics, unites the story of a boiling kettle and the fate of galaxies. It is a single, sweeping forward movement, a unity underlying all change. And though we have traced its many threads, time's arrow still has secrets to reveal, mysteries waiting in the moments yet to come. Picture yourself strolling along a quiet beach at dawn. The sky is painted with gentle hues of pink and gold as the sun begins to rise. Each step you take on the damp sand leaves a clear footprint behind you. The waves whisper in and out, touching those footprints lightly before pulling away again. When you glance back, you see the trail of prints marking where you have been, each one a memory of a step already taken. There is something curious about those footprints. They lie only behind you, never ahead. No imprint anticipates your next step. The sand in front of you is smooth and untouched, holding no hint of the path you will tread. As you continue forward, new footprints appear under your feet, moment by moment. But you cannot walk in such a way that footprints form in advance of your arrival. They come into being only as you pass, then linger as echoes of the past. In this simple morning walk, the beach is quietly teaching us about the arrow of time. The footprints are like memories pressed into the world. They preserve a record of the journey, but only in one direction, the direction from past to present. You can pause and study them, recalling which way you came, but they cannot tell you for certain where you are going. In life, just as on the sand, we leave traces of what has been, yet the future remains unmarked, a smooth expanse waiting for events to write their story. Now imagine later that morning, you find a faded photograph tucked in an old journal. You hold it gently in your hands, feeling the slight curl of its edges. In the photo, sunlight falls across smiling faces, gathered at a long-ago celebration. As you gaze at it, you realize this captured moment is a fragment of time that once was. That day is gone, except for in memory and in this image. The photograph serves as a small time machine, carrying you backward into a moment you can no longer touch, except through recollection. Yet even these records are not eternal. The footprints you left at dawn will gradually be washed away by the next high tide, or blown by the breeze until they are lost. The photograph, too, will slowly yellow, and its details may fade as the years pass. And our own memories, no matter how vivid, can blur or distort over time. The past leaves its marks on the present, but time also gently erases those marks as it marches on. Another reminder that the flow of time moves ever forward and never in reverse. The more you think about it, the more mysterious it seems. We have countless ways to recall the past. Pictures, journals, recollections in our minds, but no device or trick to glimpse the actual future with certainty. You can imagine tomorrow, but you cannot remember it the way you remember yesterday. The mind's eye can conjure possibilities, yet those are only fantasies, not true memories. Every true memory, whether in a photo or in our heads, is anchored to something that has already occurred. We are historians of our own lives, compiling albums of what we've seen and done, while the pages for days yet to come remain empty. Why is it that memory clings to the past, but not the future? It feels like an obvious fact of life. Of course we remember what has happened and not what hasn't. But when you pause to consider it, it is profoundly perplexing. Nothing in the basic laws of physics, as we learn in school, explicitly says that your coffee cup can't unshatter, or that you couldn't remember things that haven't happened. Yet somehow, in the grand scheme of the universe, events unfold only one way, and our awareness follows along. There is a one-way direction woven into the fabric of reality, and memory is one of the clearest signs of it. Think of your own memories, those precious remnants of days gone by. They reside in the intricate connections between neurons in your brain. Each experience you have, the laughter of a friend, the warmth of the sun on your face, the sound of the ocean at dawn, leaves tiny changes in the structure of your mind. Proteins are moved, synapses strengthened or weakened. Traces that encode the moment are set in place. Just as footprints emboss the sand, experiences emboss themselves into the physical matter of your brain. And like footprints, these neural impressions form as events happen, not before. The brain has no physical record of next week's laughter or tomorrow's sunrise, because those moments have not yet occurred to imprint themselves. Our biology, as much as our intuition, enforces this one-way record keeping. Even beyond our personal recollections, the world around us holds memories of what came before. The rings inside an old tree quietly count the years of seasons past, each ring a whisper of a long-ago spring or drought. A weathered trail of animal footprints by the riverbank hints at a deer's path in the night. Ancient rocks hold fossil shells of creatures that lived millions of years ago, their forms preserved in stone as a testament that they once lived and died. Everywhere we look, we find records of past events etched into the present. They tell us that something happened. Someone walked here. Something grew here. Some creature once swam in a vanished sea. But nowhere do we find inscriptions from the future waiting to be realized. Nature, it seems, only keeps journals in one temporal direction. This one-sided storytelling of the universe raises a gentle but profound question. What fundamental rule underlies this flow from past to present? Why can we see only the wake of history and never its reverse? The trail of footprints on the beach, the cherished photographs, the tree rings and fossils, all these are clues. They suggest that time itself has an orientation, a preferred way of unfolding. To uncover why, we must look at how events relate to one another. We must consider how each moment gives rise to the next. The clues of memory and records are pointing us toward the concept of cause and effect, and the realization that causes always seem to precede their effects. Where there is a memory of an event, there was a cause that made that memory. This realization leads us into the realm of cause and effect. All around us, every happening follows this gentle rule. Something occurs first to set other things in motion. In the hush of morning, a breeze stirs and carries the scent of blooming jasmine through an open window. The breeze did not arise out of nowhere. Perhaps the warming sun caused air to rise and wind to flow. And that breeze, in turn, causes the wind chime by the window to sway and ring softly. Cause then effect. The pattern repeats itself quietly in the background of our everyday world. Pause for a moment and consider how nothing truly begins without something before it. A rolling wave in the ocean is born from a distant gust of wind. The ripples of a pond trace back to a single pebble that dropped in. In a peaceful meadow, a sudden rustle in the grass draws your attention, and you realize it was caused by a small rabbit hopping by. Every effect has its cause, each moment gently pushed by the moment that came before. There is a continuity, a connectedness threading through time, where events hand the baton to to the next in a silent relay. Our lives, too, are built on this chain of causality. Think about the choices you make in a day. You decide to water a potted plant in the morning. Later, the soil is moist and the plant stands a little taller in the afternoon sun. The outcome? A thriving plant, followed from the initial act of watering. Or imagine writing a heartfelt letter to an old friend. Your decision and effort to write become the cause, and days later, when the letter arrives, the smile on your friend's face is the effect. It is always in this order: first the intention and action, then the result. We lay plans and carry them out, and only afterward do we see the fruits of our actions. Plans come before outcomes. You cannot reap a harvest before sowing the seed. It all seems so obvious that we rarely stop to marvel at it. The idea that an effect might come before its cause feels not just impossible, but utterly absurd. Picture for a moment if life worked in reverse. You find yourself holding an umbrella that is already wet before the rain has even begun. Or you receive a phone call thanking you for a gift that you have not yet sent. Such scenarios provoke a quiet, unsettling feeling because they conflict with everything our minds expect about how the world works. In reality, the rain falls first, and then your umbrella gets wet. You send a gift, and then gratitude follows. The reversal exists only in whimsical stories or dreams, never in the steady light of day. Causality is like an invisible thread that stitches the fabric of time together in one direction. We rely on it constantly, whether we notice or not. It allows us to learn from experience. Touching a hot stove causes pain, teaching us not to do it again. Even the simple act of speaking follows this logic. Our thoughts form words. We voice them, and then another person hears and understands. The hearing does not precede the speaking. There is a comforting orderliness in this, a sense that the universe honors a sequence that makes sense to us. In this order we find stability. Imagine the chaos if effect could precede cause, if the tapestry of time were woven backward and forward at random. Instead, there is a gentle forward loom to the weaving of events. Throughout nature and our lives, this forward direction of causality guides interactions great and small. A spark from a flint will ignite dry tinder, giving rise to a warm campfire, but not the other way around. The campfire's glow will then illuminate the faces around it and warm the night air. The cause, striking the flint, came first, and the effects ripple outward in time. Flame, light, and heat following from that initial spark. Everywhere we look, the story is similar. The present arises from the past, and the future arises from the present. It is a continuous unfolding. Even when we gaze up at the sky, we see cause and effect at play in a grand dance. High above, the sun's energy triggers reactions in the atmosphere, painting the morning clouds pink and orange. Later, as the day heats up, those causes might build into towering clouds and finally release rain onto the fields below. Always, the sequence holds. First the trigger, then the response. There is a rhythm to it that even the wind and clouds obey. Consider a simpler sound that drifts through the air. In a still evening, a distant church bell tolls, marking the hour. You hear its clear note only after the bell's clapper has struck the metal. That strike is the cause. The ringing sound travelling outwards is the effect. The sound arrives a few seconds later across the valley to your ears. You close your eyes and enjoy the fading echo, aware that it all began with that initial strike of the bell. Notice how in each example, something flows outward from a beginning. the bell's sound expands into the open air. A pebble's drop sends concentric ripples widening on the pond's surface. These spreading waves are themselves messages of cause and effect moving through space, carrying the news that something has happened. A bell rang here, a pebble fell there, and they carry this news forward in time, never backward. A wave travels out and eventually dies away. It does not gather itself back to return to the source in the same way. In the real world, we do not witness the water in a pond spontaneously tossing a pebble back into a hand, or the air conspiring to push a clapper so that a bell rings in reverse. Cause leads to effect, and then the moment is done as energy dissipates outward. This observation guides us gently toward another facet of time's arrow. The way things like sound and light propagate. Just as events have causes that produce outward effects, these effects often take the form of waves or signals that move in one temporal direction. We turn now to that spreading of influence, like ripples and rays streaming forward, and consider how light itself follows an arrow that never rewinds. In a dim, quiet room, a single shaft of sunlight slips through a gap in the curtains. You can see tiny dust motes dancing in that golden beam. The light has travelled far, from the sun across space, through the sky and the window, to illuminate this small indoor universe. It streams forward, ever outward, revealing specks that swirl gently in its glow. What you never see is the reverse. Dust motes suddenly plunging into darkness as the light condenses and retreats back out through the window. The sunbeam does not gather itself and return to the sun. It shines in one direction and one direction only, a ray on a one-way journey. Whenever we turn on a lamp in a dark corner of a house, we witness the same principle. The bulb glows and light pours out, flooding the walls and ceiling with a soft radiance. The objects in the room drink in that light, casting faint shadows behind them. If you switch the lamp off, the room falls dim again. But crucially, the light that had filled the space doesn't surge back into the bulb. The process is not reversible. The photons, those tiny particles of light that left the filament, have scattered and absorbed into the surroundings, gone forever from their source. You will not see the room's shadows suddenly sharpening as all the light leaps back into the lamp. The arrow of time for that glow points outward, away from its starting point. We observe this radiative arrow whenever energy spreads outwards as waves. Strike a match in a dark room, and its brief flame sends light dancing onto the walls. Long after the match is blown out, the light it emitted has travelled on. It might have bounced as a faint reflection off the walls a few times, gradually weakening with each bounce, until all of it is absorbed as gentle warmth. There is no echo of light coming back to reassemble the flame. The darkness that returns is not the light running backward. It is simply what's left when the last of the radiance has dissipated. Picture watching a film of a candle burning, but in reverse. In the backward film, you would see the room start out illuminated. Slowly, the flickering light on the walls would shrink and draw itself back toward the candle's wick. The wick would mysteriously grow longer as the flame feeds it, and finally, the match in your hand would unburn, turning back into a solid matchstick. This imaginary reverse movie is bizarre and fascinating, precisely because it contradicts reality. In our real experience, once the candle is lit, it shines outward and burns down until nothing remains but wisps of smoke and a charred wick. The light doesn't unshine, and the smoke doesn't curl back into flame. What's done is done. This one-way spread of light is so normal that we hardly think to question it. Every evening, the setting sun sends a last ray of orange across the sky, and then night falls. We know the sun's light is still out there, traveling further into space, maybe towards some distant dust cloud or a far-off world. We never expect that after nightfall, all those stray rays will converge and bring daylight back. When you look up at the stars, you are witnessing ancient light arriving at your eyes after traveling for years or centuries. That starlight began its journey long ago from its star, and it continues onward even after it passes by you. Not in a single case do we see those distant beams turn around of their own accord and rush back home. Sound behaves in much the same way. When a violin's string is plucked in a quiet hall, the music radiates outwards in waves of sound. The melody drifts to the far rows of seats and eventually fades into silence. You would never witness the hall growing loud again, because all those notes somehow decided to rush back to the violin. Once the music is played, the sound spreads and dissipates irreversibly. The silence that follows is not the sound rewinding. It is what remains after the final echoes have died away. What underlies this radiative arrow of time is the tendency for energy to disperse. Whether it's light, sound, or ripples on a pond, a disturbance will generally spread outwards from its source. It disperses into larger and larger volumes of space, becoming more thinly distributed and eventually vanishing into background noise or heat. To make all those waves come back together again would require an extraordinarily precise coordination of all the scattered pieces of the wave, so precise that nature, left to itself, never performs it. Only with deliberate effort can we sometimes corral waves backwards, for instance, using mirrors to reflect light back to a focus or walls to echo sound. But even those reflections are just redirected forward motion, not truly a reversal of time. The overall flow is still from a concentrated source outward to an ever wider realm. Think of radio signals leaving a transmitter tower. The signals rush out in all directions, carrying music or voices through the air. A radio antenna picks up a tiny fraction of that energy to deliver the broadcast to your living room. The rest continues traveling, dissipating as it goes. None of those radio waves spontaneously decide to U-turn and cram themselves back into the broadcasting tower to refill its energy. The transmission is a one-way trip. Now consider a pebble you toss into a still lake at dusk. Circular ripples expand across the water, reflecting the sky in their gentle rings. They spread out until they become too small to notice. You will not see a moment where new ripples gather themselves from the far edges of the lake and rush inward to fling the pebble back into your hand. The calm eventually returns, but not by reversing what happened, only by moving forward into a new state where the energy has dispersed. We find comfort in how dependable this behavior is. The lamp in your room lights it up every time, and never once has it pulled all the light back in like a gulp of illumination in reverse. The predictability of light and sound spreading out is part of why the world makes sense to us. It aligns with the cause and effect narrative. The cause, a shining bulb or a ringing bell, produces an effect that travels outward. It would be deeply unsettling if, say, after turning off a light, your room grew briefly brighter as all the photons raced back into the filament. Such oddities are confined to trick photography and science fiction. In the gentle reality we know, light simply goes forth and does not return of its own accord. This radiative arrow is yet another thread in time's tapestry. It ties closely to the idea of entropy, the gradual blending and spreading of energy, though we need not invoke complex terms to feel its presence. We see it in the fading twilight and hear it in the last echoes of a song. With the concept of radiating energy in mind, we can look again at the notion of loss and spreading in physical processes. Nowhere is this more apparent than in the phenomenon of friction, where motion and energy transform irreversibly into heat. So let us gently turn to the whisper of friction and how it too points us along time's single arrow. On a quiet porch at dusk, a wooden rocking chair moves in gentle rhythm. You give it a slight push with your foot and then let go. Slowly, the chair rocks back and forth with a comforting creak. Each swing is a little smaller than the last. The motion that was once lively is ebbing away. Eventually, the creaking fades and the chair comes to a standstill. Where did the energy of that motion go? It didn't simply vanish. Rather, it slipped into the world as a whisper of heat and sound. The wood of the chair's runners warmed ever so slightly where they rubbed the floor, and the air around it carried a faint sigh of a creak. What was orderly movement became scattered vibrations, dispersed and quiet. This gentle fading of motion is the hallmark of friction. Whenever an object slows down as it slides or rolls, friction is at work, transforming kinetic energy, the energy of motion, into other, more diffused forms. Imagine sliding an old book across a table in a still library. At first, the book glides silently, then it slows and comes to rest. Touch the book afterward, and you might feel it a bit warm, and the table's surface too. That warmth is the ghost of the book's motion, now living among the jostling molecules in the wood. A soft hush of sound might have accompanied the slide, a whispering scrape that quickly died out. That sound carried away a part of the motion's energy into the air. All of these little effects, a touch of warmth here, a murmur of sound there, are friction's way of telling us that energy has been scattered into countless tiny movements. Friction is the great pacifier of moving things. Left alone, almost every motion we see around us eventually succumbs to its subtle grip. A spinning top whirls with childhood delight on the kitchen floor, but after a time, it wobbles and falls over. The spin spent. The energy that once kept it upright has drained into slight warming of the floor, and a barely audible hum as it slowed. A wind-up music box plays a sweet melody when you turn its key. As it plays, the notes become slower and softer until the mechanism stops, the spring inside unwound. Feel the box, and you'll sense a bit of warmth. The mechanical energy of the music has turned into heat in the gears and casing. In each case, friction quietly takes the ordered energy of motion and spreads it out, leaving things at rest. On the microscopic level, this process is like a grand game of billiards with trillions of balls. The moving chair, or sliding book, is composed of atoms and molecules, and when it moves, those particles move in unison. That is what we call organized motion. Friction introduces a tiny randomness. The surfaces in contact are rough at a microscopic scale, so molecules collide and bounce around chaotically. With each tiny collision, a little piece of the chair's smooth motion is sliced off and given to the disordered jiggling of atoms. Bit by bit, the ordered motion dissolves into random vibrations, heat in the materials involved. If we could magnify our view to see the atoms in the chair's runners and the porch floor, we would witness an increasing frenzy of microscopic motion as the chair slows. In that world of the very small, the peaceful rocking has completely vanished into turmoil. Here is the enchanting paradox. The fundamental laws of physics that govern those collisions, the laws that atoms obey, don't actually prefer one time direction or the other. In theory, if every microscopic motion were perfectly reversed, the chair would start rocking again as all the little vibrations pushed it in unison. Nothing in the equation strictly forbids the atoms in the wood and air from conspiring to give back the energy. But in practice, such a reversal is so fantastically improbable that it might as well be impossible. The countless molecules would all need to cooperate in just the right way to impart a push to the chair together. The universe would have to run an almost infinite lottery and win every single draw. So while the micro world is reversible in principle, the macro world we experience is effectively not. Friction's whisper ensures that once energy has dispersed into a tangled chorus of molecular motions, it will not spontaneously gather itself and march back into organized form. We feel this truth intuitively. We never expect a resting object to start moving on its own, drawing energy out of cooler surroundings. A coffee mug slid across a countertop always grinds to a halt. We'd be astonished if it soaked up heat from the room and sped up instead. An ice skater gliding on a perfect rink will slow down eventually, not accelerate, unless she actively pushes again. The quiet conclusion of motion is accepted as normal, while the reverse would seem like a magical violation of everyday reality. The arrow of time, in this guise, is a one-way street from motion to heat. This transformation has a name in physics: the increase of entropy, a measure of how spread out and disordered energy becomes. You don't need to be a physicist to sense it. Whenever a process feels irreversible, entropy is usually in play. Friction generates entropy by taking the concentrated, directional energy of motion and distributing it into myriad random jostlings. Once entropy has increased in this way, the only way to make the object move again is to input new ordered energy from outside. For example, by pushing the chair anew or rewinding the music box. The universe won't do it for free, because the natural drift is toward greater disorder in energy's distribution. Thus, the whisper of friction is the voice of time's irreversibility in everyday life. In the soft hush, when a once moving thing goes still, we are hearing time's arrow in action. Each slowed wheel, each fading swing of a playground seesaw, each gradually silenced music box tune is telling the same story. It is the story of energy dispersing, of order becoming randomness. It's a quiet story, often literally a quieting, that underscores how the past and future are not interchangeable. A moving object plus cool surroundings, that was the past. A motionless object plus slightly warmer surroundings, that is the future. With friction's lesson in mind, we can look at the world and see memory in the making and unmaking, in a sense. As friction erases motion and creates heat, it also tends to erase specific details of how that motion came to be. The warmth left behind in the chair and floor carries no clear imprint of the rocking pattern that produced it. Details have been lost into the haze of heat. This theme of lost information leads us to consider how the history of things can be preserved or wiped away. Sometimes, however, the world does keep an imprint of what has come before, not in motion or heat, but in structure and information. To explore that side of time's arrow, we turn to the records written in matter itself, to the information preserved in grooves, grains, and fossils, the memories that the physical world can hold. Now the different arrows begin to interweave. Our exploration of memory, causality, radiation, and friction naturally leads us to consider information itself. Every book in a library, every fossil in the ground, every photograph in an album is a testament to the past, an echo of the arrow of time set into matter. The creation and preservation of these records obey the same fundamental rule we've been observing. To remember something, even in physical form, involves an increase in entropy somewhere, and the information once created will linger until it too eventually decays. Imagine a quiet cave hidden in the hills, where the walls are adorned with ancient handprints and paintings. By the light of a gentle fire, long ago artists pressed their pigments onto the stone, recording scenes of hunts and rituals. Those images have endured through millennia. The people who made them are gone, their voices long silenced, but a trace of their world remains in the ochre and charcoal outlines. Each handprint on the cave wall is like a greeting sent forward through time, a physical memory of a moment in the distant past. The rock carries that memory, preserving it against the erasing flow of wind and rain for as long as the cave stands. Not all records are made intentionally by human hands. Sometimes the earth itself writes history in its own quiet script. Consider a shallow, dried-up lake bed where a wandering animal left footprints in the mud ages ago. The sun baked the mud hard, and then over the years, layers of silt and sand gently settled on top, protecting those prints. Eons pass, and the mud turns to stone. Now imagine a person, in the present day, carefully brushing away the dust to reveal a fossilized footprint. In that fossil, the shape of a paw or hoof is perfectly preserved. A snapshot of a creature's passing long ago. The ground beneath us holds countless such stories. Leaves pressed into rock like nature's artwork. Bones turned to stone that speak of creatures no one has ever seen alive. Shells embedded in cliffs high above the sea, telling of ancient oceans. Each fossil and imprint is a page from time's archive, a record of life and environments that have vanished but not been completely forgotten. We humans have learned to make our own durable records of the past. Think of a diary or a history book, filled with written words that describe events. The ink on those pages is a physical arrangement, shapes that hold meaning because we all agree on the code. As long as the paper and ink survive, the information can be read and understood, even centuries later. An old photograph works similarly. Light from a moment floods a camera, and the chemical changes on film or the pattern of pixels in a digital sensor freeze that moment in place. Later, we can hold the photo or open the file and see, with wonder, the exact configuration of faces and places from that split second in time. Through such records, a moment lives on beyond its passing. Our libraries, museums, and digital archives are like external memory banks for humanity, storing the knowledge and experiences of those who came before. In the modern world, we rely on an ocean of digital bits to keep our records. Every email saved, every family photo on a hard drive, every scientific dataset in a server farm, all are encoded in the tiny states of physical devices. A flip of magnetization on a disk, a pattern of electric charges in a memory chip. These minute changes in matter correspond to ones and zeros, letters and images, the stuff of memory, though invisible and silent. A computer's storage is like a vast chronicle inscribed on silicon and metal. Think of a simple text document. As you type, electrical signals arrange billions of microscopic switches into a pattern that represents your words. That pattern, if preserved, can be opened tomorrow or years from now to reveal exactly what was written. In essence, the computer has stored your message, ready to be revived at any future time. In this way, digital technology extends the principle of physical memory into a realm of incredible density and longevity. A tiny flash drive can hold the equivalent of whole libraries, an entire trove of moments and thoughts made solid. What all these examples have in common is that they tie a present object to a past event. The cave painting links a rock face today to an artist's gesture thousands of years ago. The fossil footprint links a stone to the instant an animal stepped in mud. A photograph links a sheet of paper or a file of data to the scene that unfolded before a lens. The physical world, through these records, acquires a kind of memory. Unlike our fragile human recollections, these material memories can far outlast a single lifetime. A painted symbol on a cavern wall might persist long after any living being remembers the culture that created it, waiting for someone to decipher its meaning. In a sense, matter itself can remember, at least in fragments and clues, carrying forward information that would otherwise be lost to time. There is, however, always a cost and a condition to making such records. To carve a message into stone, or to forge a clay tablet, effort and energy must be used. Heat and other byproducts are released into the environment in the process. Even nature's own record keeping, as with fossils, requires specific conditions and often dramatic events, like volcanic ash falls or rapid burials, to preserve the imprint against the usual tide of decay. And while these records can endure, they are not truly permanent. The cave paintings can fade or be worn away over tens of thousands of years. Fossils can be broken or melted by the Earth's movements. Digital files, if not cared for and migrated to new media, can become unreadable as technology changes or if the storage medium decays. The arrow of time still courses through these objects. They too can be eroded or destroyed eventually, but on a timescale often much longer than our own lives. The key is that for a while, sometimes for an astonishingly long while, the information remains frozen in place, accessible to anyone who comes looking with the right understanding. These records give the arrow of time a kind of tangible form. They emphasize the difference between past and future. We find remnants of the past all around us, in written chronicles, in layers of rock, in data banks, but we do not find records of the future. No library contains the history of a tomorrow that has yet to happen. The physical world holds clues pointing backward, not forward. It's as if the universe is a one-way museum. It accumulates artifacts of what has been, while offering no previews of what will be. This, too, is connected to the flow of time. Only after events occur can they imprint themselves on matter. The future leaves no fossils or photographs, only possibilities. By reading these traces, we become time travelers in a sense, able to reconstruct and imagine what came before. An archaeologist holding a clay tablet can conjure the bustling marketplace or royal decree recorded in its symbols. A scientist examining a fossilized fern can picture the primeval forest where it once grew. A person scrolling through an old family album on a computer can relive moments of childhood. These experiences are made possible because information about the past was captured and carried forward. And all of it relies on the arrow of time, the forward progression that allowed something to happen and then leave a mark. Those marks persist into the future, where they can be found and interpreted. But the causality is strictly one way. The tablet did not record a future event. The fern's stone impression does not reveal a plant that will sprout years from now. The photograph doesn't show a day that hasn't dawned yet. Thus, in the grain of wood, the layers of sediment, the binary switches of a computer, the past finds a way to speak. The existence of these records is itself a product of time's asymmetry. It takes work and favorable conditions to create a lasting imprint, but no effort at all for the future to remain unrecorded. In this way, the ability to store information is yet another facet of time's arrow, intertwined with entropy, creating order in one place. An inscribed tablet, a structured database, expends energy and increases disorder elsewhere. Still, through that expenditure, we gain a precious gift, knowledge of what came before, knowledge that can survive the passing years. Our exploration of memory in matter naturally leads us to consider memory in ourselves and in other thinking beings. Just as a book or a fossil can preserve a story of the past, so do our minds preserve experiences. Yet there is something unique about the arrow of time as it is felt and processed by conscious minds. We turn our attention now from the records etched in clay and stone to the living record keeper inside us, the mind, which constantly sifts the stream of time, retaining some moments and letting others go. In the dim quiet of evening, you sit comfortably and let your mind wander over the events of the day. Memories rise up, the taste of morning coffee, a friendly conversation at noon, the golden light of late afternoon. Each recollection comes effortlessly, yet they all share one striking trait. They are of things that have already happened. As you reflect, you might also ponder tomorrow, planning what you will do when the sun comes up again. But these thoughts of the future are tentative, imagined outlines. You cannot recall tomorrow's breakfast in the way you recall today's. Your mind, rich and creative as it is, still observes the same arrow of time as the rest of the world. It stores the past, experiences the present, and anticipates the future, but it cannot remember what has not yet come to pass. Our brains are often compared to organic computers, constantly processing information. And like any physical process, thinking has an inherent direction. Consider what happens each moment in your brain. Millions of neurons fire off tiny electrical pulses, communicating signals that encode what you see, hear, and feel. These signals cascade in one direction, cause leading to effect. Light from the setting sun falls into your eyes, triggering neural responses that travel into your brain's visual centers. There, patterns of activity form an image in your mind of the sun sinking low. The sequence is always from input to perception, never the reverse. You never have the experience of a vivid image in your mind that then causes light to travel backward into your eyes and out to the sky. The chain of events, light to eye to brain to conscious impression, goes one way only, aligning perfectly with time's forward arrow. In living memory, we find another mirror of the thermodynamic arrow. To lay down a new memory, your brain must physically change itself. Proteins must be synthesized. Synapses, the connections between neurons, must be strengthened or weakened, circuits rearranged ever so slightly to encode the experience. All of this requires energy. Think of the surge in appetite you might feel after a day of intense learning or concentration. Your brain has been consuming fuel to rewire itself with new knowledge. As neurons fire and reconfigure, they release heat, just as an engine does when it works. If you place your hand on someone's forehead when they are deep in thought, you won't feel it get noticeably hot. But on a microscopic level, each act of thinking disperses a tiny bit of energy as warmth. The brain runs warm on our thoughts, a gentle glow of metabolic fire that signals the irreversibility of mental processes. You cannot unburn the calories your brain just used any more than you can unthink the experience that formed a memory. This forward working of the mind shows up in the very notion of learning and forgetting. Learning something new is often a one-way street. Once you truly understand or memorize a fact, your brain has changed and you carry that knowledge into the future. You can't simply rewind your neural circuits to a previous state without that fact, unless injury or illness intervenes, which is its own irreversible change. On the other side of the coin, forgetting also follows time's arrow. Memories gradually fade or distort if we do not revisit them. The process of forgetting might be thought of as a slow diffusion of the once sharp details of a memory, into the background of the mind. It happens over time, not all at once, and certainly not in reverse. We don't wake up gaining a memory of tomorrow. Instead, we wake up perhaps having lost a little of yesterday. There is a deep connection between why our minds work this way and the fundamental laws of physics. The increase in entropy, the spread of energy and information into disorder, underlies both the thermodynamic arrow and the psychological arrow of time. Every act of remembering has a cost. It uses up chemical resources and increases entropy in the brain's cells. Even the act of erasing a thought or letting go of a memory involves physical processes. Enzymes breaking down molecules, neuronal connections, weakening that generate waste and heat. Our very ability to think and remember is founded on irreversible steps. The neuron that fires to record a sensation cannot unfire on its own. It must reset chemically, a process that again takes time and dissipates energy. We experience time's one-way flow vividly in our mental lives. We sense the forward motion in the constant change of our thoughts and the continuous accumulation of experiences. Consider the feeling of mental fatigue at the end of a long day. That tiredness is a sign that your brain's chemistry has been altered by hours of firing synapses, depleting neurotransmitters and energy stores. Only rest and more energy intake, fresh food and sleep can restore it. You cannot simply wish your mind back into the fresh, untired state it had in the morning without going through the restorative processes that take time. In essence, the weariness of the mind is like the wear of a physical machine, a reminder that time's arrow leaves its mark on our mental as well as physical state. Our subjective sense of time also flows in line with these physical changes. We feel time moving forward because our thoughts move forward, each moment of awareness following the last, building upon it or reacting to it. You may have noticed how difficult it is to truly live in the present. The mind is always in motion, carrying impressions from moments before and projecting inklings into moments to come. This forward bias is so ingrained that we hardly question it. We remember what has happened, we act in the now, and we imagine what might happen later. The flow of consciousness is like an arrow streaming from past to future, never the other way around. In a very real sense, our minds are time-bound instruments. Every memory, every idea, every decision is embedded in the flow of time, conditioned by what came before and influencing what comes after. When you make a choice, say, to speak a kind word to a friend, that decision arises from a chain of prior thoughts and feelings, and once made, it sets in motion new events. Your friend's smile, perhaps, and the memory of that interaction for both of you. You cannot reach into the future to decide first and let the cause follow. Cause in the mind, as in the physical world, precedes effect. Neuroscientists find that even the brain's routines for keeping time, the circadian rhythms that make you sleepy at night and alert in the morning, or the way you estimate seconds and minutes passing, are anchored in biochemical cycles that themselves run forward and not backward. Everything in the brain, from the level of ions trickling across neuron membranes to the broad patterns of neural activity that constitute a thought, obeys the direction of increasing entropy and one-way causality. This is precisely why our mental arrow of time aligns with the thermodynamic arrow. The brain is made of matter and energy, and it can do no better than to follow the same physical rules. Yet, within these bounds, the mind creates something remarkable, the sense of continuity and narrative that forms our life story. We continuously knit together the past as we remember it, with the present moment and our expectations of the future. This storytelling is only possible because of the stable records our brain keeps, our memories, and because time moves forward, giving those records context and sequence. The mind's narrative unfolds in order. To rearrange it out of time's order is the realm of imagination or fiction, not reality. We can imagine what it might be like if time flowed differently, but we cannot make our minds actually live it. In summary, the arrow of time runs through our very thoughts. Our brains, like all things, convert order to disorder as they work, leaving us with rich recollections of the past and the irreversible passage of each experience. This understanding, that even our thoughts pay homage to time's one-way march, leads naturally to questions about information and computation. After all, brains are not the only systems that manipulate information. Our computers do so as well, and they too must obey time's arrow. To delve deeper into why erasing a memory or a bit of data has a fundamental cost, we will explore the one-way rules of computation and how forgetting even the smallest piece of information adds to the universe's ledger of entropy. Picture a busy computer server room filled with racks of processors blinking with tiny lights. The air is kept cool by whirring fans, all because those processors are constantly releasing heat. Every computation they perform, every bit of data they store or erase, adds a little warmth to the room. Even your own laptop grows warm on your knees after you've been browsing and typing for a while. This warmth is no mere byproduct of inefficient engineering. It is fundamentally linked to the way information is processed. In fact, there is a law of nature, discovered by physicist Rolf Landauer in the 1960s, that tells us something profound. Whenever you erase a bit of information, you must generate a bit of heat. To understand why, imagine a simple scenario. You have a tiny memory device that can hold one bit, either a 0 or a 1. When you deliberately reset that memory to 0, regardless of whether it was previously 0 or 1, you are erasing whatever information was there. In doing so, you are taking two possible states, the prior uncertainty of not knowing if it was 0 or 1, and forcing the system into one definite state. That reduction in uncertainty, in information, has to go somewhere. The laws of physics demand that it be paid for by an increase in entropy, usually in the form of heat released to the surrounding environment. Landauer quantified this minimal cost. At room temperature, erasing a single bit inevitably releases a tiny puff of heat, on the order of 1 joule. It's an unbelievably small amount, but multiply it by the trillions of bits being flipped and erased in computer chips all over the world each second, and it becomes very real. Whenever you hit delete on a file, or when a computer program overwrites a chunk of memory, nature's fee for that forgetting is paid in heat. That is why heavy computation requires cooling. It's not just a practical issue of current technology. It's rooted in fundamental physics. We could, in theory, design computers that do fewer unnecessary erasures, so-called reversible computing, which would generate less heat. But as long as some information is being discarded, and any useful computation ultimately must discard bits to produce a clear result, there will be a thermal price to pay. The arrow of time in computation is revealed by this price. You can't unscramble an egg, and likewise you can't compute, in the usual way, without increasing entropy somewhere. An illustrative analogy is writing on and wiping clean a chalkboard. Writing some information with chalk arranges dust on the board in a meaningful pattern. Say you write a simple math equation. The chalk lines now embody a message on the board. When the lesson is over and you erase the chalk marks, the information disappears from the board, but not without a trace. The act of erasing creates a little cloud of chalk dust and warms the surface of the board ever so slightly from the friction of the eraser. The information has been lost from the organized pattern on the board, but the physical effects, the dust and heat, carry that entropy into the environment. In the digital realm, erasing a bit isn't done with a physical eraser, but the principle is the same. The entropy must go somewhere. A computer chip dissipates heat in the moment it resets bits, just as surely as the chalkboard warmed under the eraser. This connection between information and entropy was long suspected by physicists pondering the foundations of thermodynamics. It provides the resolution to one of the famous puzzles of physics, Maxwell's demon. This thought experiment imagined a tiny intelligent creature, the demon, that could watch gas molecules and open or close a door to sort fast molecules from slow ones, seemingly creating a temperature difference and violating the second law of thermodynamics. For a time, it looked like the demon could cheat entropy. But along came the realization that the demon itself must record information about each molecule to do its trick, and eventually it has to erase or forget that information to be ready for the next round. When the demon erases its memory, it pays the Landauer price in heat, which ends up restoring the entropy it had apparently removed. The second law remains safe and sound. The demon, like every other process, cannot break the fundamental arrow of increasing entropy. But along came the realization that one cannot cheat thermodynamics, even with clever information handling. In the end, even Maxwell's demon must bow to the second law. Cleverness and information cannot circumvent the fundamental arrow pointing toward higher entropy. The second law remains safe and sound. The demon, like every other process, cannot break the fundamental arrow of time. The principle that deleting information creates heat links the abstract world of bits to the concrete world of energy. It tells us that forgetting is a physical act. When your computer's hard drive controller decides to overwrite old data with zeros, the very atoms in the circuitry jostle and vibrate a bit more, shedding that excess energy as thermal motion. Even in brain cells, as we considered earlier, letting go of a memory, albeit through a different mechanism, involves molecular changes that release energy. Of course, one lost memory doesn't noticeably warm your head the way a running laptop warms your lap, because biology works differently and the scales are different. But the underlying truth is shared. Whether in a machine or a mind, disposing of information has an irreducible thermodynamic cost. Is it possible to avoid this cost? Only in theory. Scientists have conceived of reversible computers, devices that would compute without ever erasing bits, so that no entropy would be generated. In practice, however, computations that do anything useful must eventually discard information, if only the unwanted portions of results and temporary data. Real-world computers, from the simplest calculator to the most advanced quantum computer, all ultimately generate some heat as they reach definite outputs. As a result, the computational arrow of time remains firmly in place. Despite our cleverness, we cannot sidestep the thermodynamic price of processing information. To put this into perspective, the flow of information in our modern world has become a significant driver of energy use. And all of that energy eventually turns into heat. The countless data centers, network routers, and personal devices around the globe draw electricity to process bits and bytes, and every bit of it ultimately dissipates warmth into the environment. Every email sent, every photo deleted, and every search query answered adds an almost imperceptible increment to the world's entropy. In aggregate, the intangible world of digital information leaves a tangible thermodynamic footprint on our planet. It's a humbling reminder that even our advanced technologies obey the same one-way rules of nature, contributing their small share to the ever-increasing entropy of the universe. We live in an age where huge servers hum with activity and millions of smartphones warm our pockets. Each is a little engine of entropy, taking in energy to process information and shedding a bit of that energy as heat when information is discarded. The next time you feel a computer chip or phone that's warm to the touch, you're feeling the arrow of time in action at the information level. It's the heat of logic and memory, the gentle warmth of countless bits being irreversibly set and reset. This union of information theory and thermodynamics reinforces the interconnectedness of all the arrows we've been exploring. They are all tied to the same fundamental principle, the universe's tendency toward higher entropy. It is the same fundamental truth behind radiating light, friction's heat, and the cost of erasing memory. As we move to our final perspective, we can gather together these threads of memory, signals, and heat, and see how they weave into one consistent picture of time's arrow. All the different arrows of time we have explored, the remembering of the past, the chain of cause and effect, the one-way spreading of light and sound, the quiet dissipation of friction, and the cost of erasing information, are not isolated quirks. They are threads of one grand tapestry, all woven together by the same underlying principle. In each case, something goes from a state of order to a state of disorder. Energy spreads out. Information is lost to heat. Patterns become scrambled. We recognize this as the increase of entropy, the fundamental trend that gives time its direction, the reason a footprint, a cooling cup of tea, a fading memory, and a computing circuit all march forward, is that, in each, a bit of the world's order is turning into disorder, irreversibly. Consider, for example, a simple mishap. You are holding a porcelain cup of tea and it slips from your fingers. The cup falls and shatters on the floor. In that brief moment, all the arrows of time reveal themselves. Your memory of the cup exists up until the moment before it fell. Afterward, you can only recall the event, not foresee it. The cause, the slip, comes before the effect, the broken cup. The crash sends sound waves ringing through the air, spreading outward and never gathering back. The cup's orderly form is lost, its pieces scattered, its heat and sound dissipated into the room. You can sweep up the fragments and perhaps keep them, but you cannot reassemble the cup as it was. The event is irreversible. A humble kitchen accident encapsulates time's one-way flow in miniature. It is astonishing, in a way, that so many aspects of our experience, from the cosmic scale of starlight to the intimate workings of our minds, share the same arrow. A star shines, and its light travels outward, never to reconverge. A living creature is born, accumulates memories and wear, and eventually ages, never growing younger. Each process is different in detail, yet all obey the same temporal orientation. This unity tells us that time's arrow is something deeply built into the fabric of reality, not just a coincidental feature of one phenomenon or another. It arises from the conditions of our universe as a whole. Physicists believe that the key lies in the way the universe began. The story goes back to the very dawn of time, to the Big Bang and the state of the young cosmos. By all indications, the early universe was an extremely hot, dense, yet surprisingly ordered place. It had incredibly low entropy relative to what it could have been. That initial order is like a primed canvas on which the arrow of time could begin painting. As the universe expanded and cooled, entropy began to increase. Structures formed and then decayed. Concentrations of energy spread out. Over billions of years, stars have burned their fuel, galaxies have drifted and merged, and in pockets of the universe like our planet, life emerged and started doing its own complex dance under time's arrow. All of this unfolding drama has been a journey from an initially ordered state toward increasing disorder. And that journey continues even now, as the cosmos carries on evolving and dispersing energy. Why the universe started in such an ordered condition is a profound mystery. It is one of the great unanswered questions in physics. Some suggest that it might be a result of deep laws of cosmology or something special about the Big Bang, while others admit we simply don't yet know. But what we do know is that this low entropy beginning is the ultimate source of the arrows of time we experience. Because the universe began in a state of high order, there has been a direction for time to roll downhill, so to speak, ever since. Every cup of coffee cooling, every memory forming, every star shining is participating in this grand, one-way evolution that started at the beginning of time. When we look at the world through this lens, we see time's arrow everywhere. It is in the cracks of ancient rocks and the light of distant galaxies, in the decay of old wood and the sparks in a computer chip. It connects the gentle fading of a day's light to the ticking of your thoughts and the warmth of a busy city at night. All are manifestations of the same cosmic progression. We, as thinking beings, ride this river of time along with everything else, carried from what was to what will be. Understanding that these arrows are really one can change how we view our everyday phenomena. The next time you watch ice melt in a glass, or see a trail of footprints on the beach gradually washed away by the tide, you might recall that these humble events are playing out the very same principle that governs the aging of the stars and the expansion of the universe. There is a profound continuity in it. This is a reassurance that our small experiences of time's passage are connected to the grand story of the cosmos. As our journey through the arrows of time comes, all the different arrows of time we have explored, the remembering of the past, the chain of cause and effect, the one-way spreading of light and sound, the quiet dissipation of friction, and the cost of erasing information, are not isolated quirks. They are threads of one grand tapestry, all woven together by the same underlying principle. In each case, something goes from a state of order to a state of disorder. Energy spreads out, information is lost to heat, patterns become scrambled. We recognize this as the increase of entropy, the fundamental trend that gives time its direction. The reason a footprint, a cooling cup of tea, a fading memory, and a computing circuit all march forward is that, in each, a bit of the world's order is turning into disorder, irreversibly. Consider, for example, a simple mishap. You are holding a porcelain cup of tea, and it slips from your fingers. The cup falls and shatters on the floor. In that brief moment, all the arrows of time reveal themselves. Your memory of the cup exists up until the moment before it fell. Afterward, you can only recall the event, not foresee it. The cause, the slip, comes before the effect, the broken cup. The crash sends sound waves ringing through the air, spreading outward and never gathering back. The cup's orderly form is lost, its pieces scattered, its heat and sound dissipated into the room. You can sweep up the fragments and perhaps keep them, but you cannot reassemble the cup as it was. The event is irreversible. A humble kitchen accident encapsulates time's one-way flow in miniature. It is astonishing, in a way, that so many aspects of our experience, from the cosmic scale of starlight to the intimate workings of our minds, share the same arrow. A star shines, and its light travels outward, never to reconverge. A living creature is born, accumulates memories and wear, and eventually ages, never growing younger. Each process is different in detail, yet all obey the same temporal orientation. This unity tells us that time's arrow is something deeply built into the fabric of reality, not just a coincidental feature of one phenomenon or another. It arises from the conditions of our universe as a whole. Physicists believe that the key lies in the way the universe began. The story goes back to the very dawn of time, to the Big Bang and the state of the young cosmos. By all indications, the early universe was an extremely hot, dense, yet surprisingly ordered place. It had incredibly low entropy relative to what it could have been. That initial order is like a primed canvas on which the arrow of time could begin painting. As the universe expanded and cooled, entropy began to increase. Structures formed and then decayed. Concentrations of energy spread out. Over billions of years, stars have burned their fuel, galaxies have drifted and merged, and in pockets of the universe like our planet, life emerged and started doing its own complex dance under time's arrow. All of this unfolding drama has been a journey from an initially ordered state toward increasing disorder. And that journey continues even now, as the cosmos carries on evolving and dispersing energy. Why the universe started in such an ordered condition is a profound mystery. It is one of the great unanswered questions in physics. Some suggest that it might be a result of deep laws of cosmology or something special about the Big Bang, while others admit we simply don't yet know. But what we do know is that this low entropy beginning is the ultimate source of the arrows of time we experience. Because the universe began in a state of high order, there has been a direction for time to roll downhill, so to speak, ever since. Every cup of coffee cooling, every memory forming, every star shining is participating in this grand, one-way evolution that started at the beginning of time. When we look at the world through this lens, we see time's arrow everywhere. It is in the cracks of ancient rocks and the light of distant galaxies, in the decay of old wood and the sparks in a computer chip. It connects the gentle fading of a day's light to the ticking of your thoughts and the warmth of a busy city at night. All are manifestations of the same cosmic progression. We, as thinking beings, ride this river of time along with everything else, carried from what was to what will be. Understanding that these arrows are really one can change how we view our everyday phenomena. The next time you watch ice melt in a glass, or see a trail of footprints on the beach gradually washed away by the tide, you might recall that these humble events are playing out the very same principle that governs the aging of the stars and the expansion of the universe. There is a profound continuity in it. This is a reassurance that our small experiences of time's passage are connected to the grand story of the cosmos. As our journey through the arrows of time comes to a close, we find ourselves returned to a singular idea, that the flow of time is rooted in the tendency of the universe to move from order to disorder. Each arrow we followed pointed back to this common source. But this is not truly the end of the story. It opens up further wonder. Why should the universe have been so ordered at the start? What does it mean for the far future, as entropy continues to rise? These questions beckon us onward, inviting us to look deeper into the nature of time itself. Some scientists have speculated about what the arrow of time might mean in the far future. If the universe continues to expand and entropy keeps increasing, a day may come, trillions upon trillions of years from now, when nearly all usable energy is spent. In this hypothetical far future state, often called heat death, everything would be spread thin and even, with no gradients to drive change. Time's arrow would effectively lose its power there, because there would be no more order left to unravel into disorder. No stars would shine, no life would stir, and no new memories would form. for there would be no free energy to fuel them. It is a distant and melancholy vision, the ultimate fulfillment of the second law's promise, and yet that fate is almost unimaginably far off, and the cosmos has a great deal of story left to tell before then. For now, time's arrow remains vital and unyielding, propelling galaxies, life, and every ticking second of our experience forward. So, as we stand here, aware that we remember yesterday, but not tomorrow, warmed by the gentle irreversibility of all our actions, we can appreciate the subtle connections linking our lives to the stars above, the arrow of time, threading through memory, causality, and thermodynamics, unites the story of a boiling kettle and the fate of galaxies. It is a single, sweeping forward movement, a unity underlying all change. And though we have traced its many threads, time's arrow still has secrets to reveal, mysteries waiting in the moments yet to come. Time flows onward for us all, or so it seems. We imagine a cosmic clock in the background, ticking off seconds uniformly everywhere, binding the universe in a single rhythm. In our everyday experience, this feels true. A moment with a friend, a shared laugh, appears to unfold under the same sky and in the same time for both of you. But as we step beyond the familiar and peer into the deeper nature of time, this comforting image begins to dissolve. The universe, vast and strange, holds no single master clock. There is no universal now that synchronizes the cosmos. Not long ago in the history of ideas, the flow of time was assumed to be absolute. Sir Isaac Newton imagined time as a grand, ever-uniform current, a single drumbeat marching the entire universe forward. In Newton's view, even if our clocks ticked differently or stars moved at varied speeds, the true cosmic time rolled on unaffected, the same everywhere. This concept comforted centuries of thinkers and fits our common sense. But nature had subtler plans. In the early 20th century, Albert Einstein's theory of relativity shattered that simplicity. Einstein revealed that time is not separate and absolute at all, but bound up intimately with space and motion. According to relativity, space and time are part of one seamless fabric. Events that happen out in the cosmos do not carry a single universal timestamp. Imagine two distant stars that explode into supernovae at nearly the same time. An astronaut drifting in one part of space might witness the first star's burst and then the second's. Another observer moving rapidly elsewhere could just as easily perceive the second explosion occurring before the first. There is no contradiction. Each observer has their own valid chronology. Simultaneity, the sense of meanwhile across the universe, is not an absolute truth, but a matter of perspective. What is now for one can be earlier or later for another, depending on how and where they move. Even the pace of time itself can differ from one vantage to another. A traveller moving at extraordinary speed ages more slowly than those left behind. This is the gentle strangeness of time dilation. If you flew on a fast starship and returned home, you might discover that years passed for your friends, while only months passed for you. Yet for you, nothing peculiar seemed to happen at all. Each second of your journey felt like a second. Your heartbeats, your thoughts, the ticking of your onboard clock, all marched forward normally from your own point of view. Time can stretch and diverge between observers, but it never runs backward for any of them. However relative and flexible time may be, for every traveller, it keeps moving ahead. In the Einsteinian picture, every object carries its own clock and follows its own path through the fabric of space-time. This path is often called a world line, the unique thread of one's existence winding through the 4 dimensions of space and time. Each world line has its personal time parameter ticking forward, marking out a sequence of events from birth to death, from origin to destination. No world line loops backward on itself or zigzags against the flow. It always stretches from past to future. We all move along our world lines, each step creating a personal history. The cosmos does not grant a universal present, but it does allow every traveller their own continuous journey onward. Even without a universal now, the universe has a strict rule for cause and effect. At the heart of this rule is the speed of light, a cosmic speed limit that nothing can break. If you think of time's arrow as the direction of possible influences and events, then that arrow is built into the geometry of space-time itself. Picture each event in the universe, like a flash of light or a clap of thunder, as a point in space-time. From that event, a kind of expanding bubble of influence spreads out at light speed, reaching more and more places as time goes on. This expanding bubble defines what can possibly happen next as a result of that event. In the language of physics, we call it a light cone. To visualize a light cone, imagine a quiet pond at night. Drop a pebble in and watch ripples expanding outward. Each ripple marks where the pebble's influence reaches over time. Now imagine a flash of light in the darkness of space. One moment, it's at a point. A moment later, its influence, a shell of light, has spread out a little farther. With each passing second, the shell expands like an ever-growing bubble. If we could draw an outline around all the places that flash of light will touch as time moves forward, that outline in space-time would form a cone shape emanating from the event. Everything inside that cone is lit eventually by the flash and can feel its effects. Everything outside remains untouched, as if the flash never happened. That cone is the boundary between what the event can influence and what it cannot. Every event also has a past light cone, the counterpart that encompasses all influences that could reach that event. Just as the flash's light can only brighten certain areas in the future, it could only have been sparked by things within its past reach. If something lies outside that past cone, no signal from it could have arrived in time to cause the event. This dual cone structure, past and future, gives a precise meaning to before and after. Consider our own sun. If the sun were to flicker or flare, Earth would not know until about 8 minutes later, when the light and change arrive. Those 8 minutes are the gap between cause and effect enforced by the light cone. Nothing on Earth could respond to the sun's change before those minutes pass, because Earth is outside the sun's immediate light cone until the signal arrives. In general, for one event to influence another, it must lie within the other's light cone. This ensures a universal consistency. An effect cannot precede its cause. The geometry of space-time won't permit it. Every world line, which is an object's trajectory through space-time, is confined by these light cones. No material thing or information can race ahead of light and leave its cone behind. Even a beam of light itself traces the cone's very surface, never faster. Anything with mass, like you or me, moves more slowly, which means our world lines stay comfortably inside the cone, always pushing upward into the future. In a space-time diagram, this is like an arrow that leans a bit as it moves upward, but never tilts so far that it points backward in time. We can wander in space, take any path we like, but we cannot wander backwards in time. However we roam, we inevitably carry on into tomorrow, rather than yesterday. The result is that the arrow of time emerges naturally from space-time's structure. Instead of a cosmic decree telling the universe which way to flow, it is the web of light cones and world lines that defines what forward means. Future is simply the direction in which influence can propagate. Past is where influences came from. All observers, no matter their state of motion, must navigate within this same network of cause and effect. They may slice up now differently, but none can alter the fundamental order. Causes lie in past cones, effects in future cones. Thus, the geometry of the universe quietly upholds a consistent arrow of time. It's an arrow drawn not by an external hand, but by the very speed limits and connections that weave reality together. In the architecture of the cosmos, gravity plays a profound role in time's one-way journey. After the initial moments of the universe, as matter began to spread out, gravity gently started to draw that matter back together into clumps. What was once an almost even mist of particles slowly gathered into denser clouds. Over immense stretches of time, those clouds collapsed further, igniting as stars and collecting into galaxies. Gravity, the familiar force tugging apples to the ground, became an artist on a cosmic stage, sculpting structure and patterns out of what was once nearly uniform. As the universe ages, we see more and more intricate cosmic arrangements forming under gravity's influence. This emergence of structure is one of the grand narratives written by time's arrow. On the face of it, gravity's handiwork appears to reverse the typical trend of increasing disorder. We watch gas that was scattered becoming a concentrated star. It seems like chaos coalescing into order. A swirling galaxy with spiral arms is far more organized than the diffuse haze that preceded it. If time's arrow is supposed to lead toward disorder, why does the universe grow these magnificent structures as time passes? The answer lies in the subtleties of what we mean by disorder. When gravity pulls matter together, it doesn't do so neatly or without cost. The process releases energy, often in the form of heat or light, and that energy spreads into space, contributing to the overall increase of entropy disorder in the universe. In other words, gravity can locally create order by building a star or a galaxy, but in doing so, it also creates a greater amount of disorder elsewhere. The total entropy still rises. Consider the birth of a star from a collapsing cloud of gas. Initially, the gas is cool and diffuse. As gravity pulls it inward, the gas particles fall and collide, converting gravitational energy into heat. The forming star's core grows hot and bright. By the time the gas has settled into a shining star, it has created a highly organized object, a ball of searing plasma with layers and nuclear reactions at its heart. Yet to reach this state, the collapsing cloud radiated a tremendous amount of energy. Infrared warmth and X-rays streamed out as the protostar heated up, carrying entropy away into the wider universe. The star is an oasis of order, but the environment around it has been stirred and warmed in the process. Similarly, as galaxies assemble, gases compress and heat. Shockwaves ripple through interstellar space, and immense amounts of heat and light are released. The structured galaxy that results is accompanied by a bath of background heat and radiation, evidence that entropy has increased overall. Thus, the rise of structure under gravity doesn't violate the arrow of time. It is part and parcel of it. Gravity transforms one kind of disorder into another, all the while ensuring the net disorder keeps growing. Indeed, from a certain perspective, gravity has its own way of increasing entropy. A perfectly uniform spread of matter, say a gas evenly filling space, sounds very random, but in gravitational terms, it is actually an orderly, low-entropy arrangement. There are countless more ways for that matter to clump up into stars and planets, and for the excess energy to be flung off as heat than to remain perfectly smooth. So as time progresses, the universe naturally shifts from that special uniformity toward a clumpier, hotter, more mixed state. In simple terms, matter bunches together and energy smears out. This is a direction of increasing gravitational disorder, even though to our eyes it looks like structures forming. Put another way, each time gravity creates structure, it leaves behind even more chaos in the form of dispersed energy. The paradox resolves when we consider the whole picture. Gravity's order is local and visual, while disorder still increases globally in less visible forms like diffuse heat. For billions of years, gravity has been gathering cosmic material into ever more complex forms, a one-way progression that marks time's passage. We can tell which way time flows in our universe, partly because we see this cumulative construction. Stars light up where there were none. Galaxies grow from shapeless clouds. Each new formation, each cluster of galaxies that emerges, is a witness to time's irreversibility. It would be unfathomable to see these structures spontaneously unbuild themselves back into a featureless haze. That simply doesn't happen naturally. It would be as strange as watching broken pieces of a vase leap up and reassemble. Instead, gravity's ongoing work gives the cosmos an arrow of development, from simplicity to structured complexity. This arrow is intimately tied to another grand story of time, the expansion of the universe itself, which provides the ever-changing backdrop for gravity's creations. In parallel with the formation of stars and galaxies, the very stage on which cosmic history unfolds has been stretching out. The universe itself is expanding. Since the fiery birth of the cosmos, space has continuously grown larger, carrying galaxies with it like driftwood on a vast, swelling ocean. Over billions of years, distances between clusters of galaxies have increased. Photons, particles of light, have been stretched to longer wavelengths by this expansion, their once blazing energies diluted to a gentle glow. The cosmos that was once small, dense, and hot has become vast, diffuse, and cooler. This steady expansion is a fundamental arrow of time on the grandest scale. One clear sign of this cosmic arrow is the cooling of the universe's background light. In the early epoch, space was filled with a brilliant glow from the hot plasma of the young cosmos. As the universe expanded, that light stretched and weakened, transitioning from a fierce blaze to a faint afterglow. Today, the entire sky is suffused with this gentle remnant, microwave whispers that are the echo of a once fiery ocean of light. That afterglow's temperature has dropped over time, from thousands of degrees to just a few degrees above absolute zero. Such cooling is only possible because the universe has been growing and diluting. It's a permanent change. The universe will not spontaneously heat back up to that earlier brilliance. The direction of time is written in this cooling trend. Once hot and dense, now ever more cool and sparse. The expansion also provides more space for disorder to spread out. As galaxies drift apart and volumes grow, heat and particles have ever more room to disperse. The second law of thermodynamics, the rule that entropy tends to increase, finds a vast playground in an expanding universe. An isolated hot gas in space will cool as it expands, and once cooled, it will not compress and heat up again on its own. Similarly, the universe's overall expansion is like a one-time expansion of all cosmic matter and energy. It moves from concentrated to diffuse. If we were to imagine time running in reverse, we'd see galaxies crowding back together and the background heat intensifying, a cosmos winding itself back up. But in reality, we see it unwinding. Every distant galaxy that slips farther away, Every wavelength of light that stretches a bit more reinforces the forward march of time. There is no hint that this process will spontaneously reverse. The universe's growth is one-way traffic. In fact, rather than slowing down or reversing, the expansion has been accelerating in recent cosmic times. Galaxies far from us are receding ever more quickly, driven by a mysterious influence we call dark energy. This accelerated expansion means the universe's trend toward cooling and thinning out is not just continuing, but speeding up. It is as if the cosmos is eager to keep moving forward, making any reversal even more unthinkable. All signs tell us that the cosmic arrow, the growth and cooling of space, points unwaveringly in one direction. In the deep past, the universe's story begins in a state of remarkable uniformity. Imagine the entire cosmos as a brilliant, hot fog where matter and light were smoothly blended. Everywhere you looked, had there been anyone to look, you'd see nearly the same density, the same temperature, an almost featureless glow. This was the universe shortly after its hot dawn, a young cosmos that, despite its seething energy, was surprisingly even and calm in its structure. There were no stars, no galaxies, not even atoms yet, just a vast ocean of particles and radiation, spread out almost evenly with only the tiniest of ripples. It's a picture of near perfection, like a glassy sea at sunrise before the winds pick up. Yet, this early smoothness was not absolute. It held faint imperfections like tiny stirrings on a calm pond. In that primeval glow, some spots were just a touch denser or hotter than the average, while others were a touch thinner or cooler. These differences were incredibly small, just 1 part in 100,000 or so. You could liken it to an almost flat beach with grains of sand piled a hair higher in a few places. These minute irregularities might seem insignificant, but they were destined to become immensely important. We have actually observed their imprint directly. The cosmic microwave background radiation, the afterglow of that hot dawn, carries a delicate patchwork of slightly warmer and cooler spots. Those spots are the echoes of those original tiny variations. In an otherwise uniform sky, they are the subtle freckles of the universe's baby picture. Over cosmic time, those tiny variations grew into the structures we know today. Where there was a slightly denser patch in the early universe, gravity had just a little more to work with. That patch pulled in more and more matter as the universe expanded and cooled. A few 100 million years after the hot dawn, the first stars kindled in those denser regions. They gathered into infant galaxies. The thinner spots, by contrast, became cosmic voids, places left almost empty as matter flowed away toward the denser zones. In this manner, the almost imperceptible ripples of the early universe became a vast, clumpy network of galaxies and clusters strung across space. The grand pattern of the modern universe, the cosmic web of filaments and voids, is essentially the amplified imprint of those primordial seeds. What was once smooth has evolved into something richly structured, all guided by the arrow of time and the pull of gravity acting on those initial imbalances. This original smoothness is profoundly linked to why the arrow of time points forward at all. The early cosmos, in its simplicity, was like a wound-up spring of order ready to uncoil. It held an immense capacity for entropy to increase. Had the universe started out highly disordered, there would have been far less room for things to change irreversibly. But instead, it began in an extraordinarily low entropy state, especially in terms of gravity and structure. From that special beginning, there was essentially nowhere to go but toward more disorder. Why the universe began in such an ordered way remains an open question, one of the deep wonders of cosmology. It's as if the universe awoke in a calm arranged state, and from that calmness, time's arrow emerged, bringing on the winds of change. The smooth dawn set the stage for everything that followed. These included the growth of complexity, the flow of heat, and the clumping of matter, all the irreversible processes that distinguish past from future. Amid the grand cosmic landscape, there exist objects that embody irreversibility to an extreme. Black holes. A black hole forms when matter, say a massive star, collapses under its own gravity so completely that it creates a region from which nothing can escape. Not even light can climb out of such a region, which is why we call it a black hole. At the boundary of a black hole, the event horizon, one crosses a threshold of no return. Passing through that invisible surface is like stepping beyond a point where all roads lead inward. Once inside, there is no possible way to turn around or send a signal back out. It's a one-way journey deeper into darkness, an ultimate sink where whatever falls in is effectively lost to the rest of the universe. Black holes thus represent a kind of cosmic one-way door. If you drop something into a black hole, whether a rock, a spaceship, or a beam of light, that object is gone from our universe's perspective, seemingly erased from view. There is no retrieval, no way to undo the action. In a sense, it makes tangible an aspect of time's arrow. It's far easier to destroy information or structure than to recover it. Crossing the horizon is like crossing over an absolute boundary between before and after that cannot be retraced. We can think of analogies. Imagine a waterfall plunging into a dark abyss. Anything carried over the edge is swept irrevocably into the depths. Or picture a line on the ground that, once stepped over, cannot be stepped back. That is what the event horizon is, a line drawn in space-time that you can cross only once, inwards. This irreversibility gives black holes a special place in the story of time's one-way flow. What happens to time itself near and inside a black hole is also extraordinary. At the event horizon, the flow of time and the pull of space become tangled. For someone falling through, moving forward in time essentially means moving deeper into the hole. Once inside, all paths, all possible futures, lead inevitably to the central singularity, the final collapse point. It's often said that inside a black hole, the roles of space and time swap. Just as we cannot stop time from flowing forward, inside the horizon, one cannot stop the inevitable fall toward the center. In other words, going forward in time within a black hole literally drags you further in. The singularity ahead is as certain as tomorrow's sunrise, and in that tragic certainty lies another echo of the arrow of time. There is an inescapable fate, a directionality to events that cannot be reversed. In the universe as we know it, black holes only ever form and grow. We do not observe them spontaneously turning back into the stars or clouds they came from. A massive star's collapse into a black hole is effectively a one-way process, like an egg breaking, with no hope of reassembly. In this way, black holes serve as cosmic tombstones of order. Whatever falls in increases the hole's mass and entropy, and the details of what went in seem to be irretrievably mixed and hidden behind the horizon. And yet, modern physics has uncovered a twist to this story. Black holes might not be entirely eternal prisons after all. They can, very slowly, leak energy back out. The late physicist Stephen Hawking theorized that black holes emit a faint thermal glow, now called Hawking radiation, due to quantum effects at the horizon. Over inconceivably long times, a black hole could evaporate away into this delicate light. This prospect brings to light a quiet but profound puzzle. If a black hole eventually disappears, Where does all the information of the things it swallowed go? Is it truly lost forever, or somehow encoded in the outgoing radiation? The laws of quantum physics insist that information cannot be destroyed completely, so this remains a deep mystery. It is a subtle question, perched at the edge of our understanding, a final frontier in reconciling the arrow of time with the principles of information and quantum theory. In scientific terms, information refers to the specific details of a physical system, the unique arrangement of particles, the quantum states that distinguish one thing from another. Normally, even if something is destroyed or scrambled, we believe the information isn't truly erased, it's dispersed. For example, if you burn a piece of paper, it turns to ash and smoke. But in principle, if one had complete knowledge of every smoke particle and photon of heat released, one could theoretically reconstruct what was written. The information is still there in the universe, just in a highly jumbled form. This idea stems from the laws of quantum physics, which are time-reversible at their core, meaning they never truly delete information. But a black hole swallowing something seems to challenge this principle. When our piece of paper falls into a black hole, for all practical purposes, its information appears to vanish completely behind the horizon. And if the black hole then evaporates away, one might worry that the information is gone for good, not just scrambled, but obliterated. This is the heart of the black hole information paradox, a collision between the irreversible nature of black holes and the otherwise reversible laws of quantum physics. Physicists have been grappling with this paradox for decades. Many suspect that nature finds a way to preserve the information after all, even if in a form nearly impossible to recognize. One leading idea is that the surface of the black hole, its event horizon, might somehow encode everything that falls in, like a kind of hologram. As the black hole radiates and shrinks, the faint Hawking radiation could carry away bits of that encoded information, subtly imprinting the outgoing particles with the clues of what was inside. If this is true, then in principle, nothing is truly lost. The information comes out, but extremely scrambled and diluted. Another possibility is that when the black hole finally dies, it might release some final burst or remnant that contains the missing information. At this point, nobody knows for sure. The paradox remains unsolved, pointing toward new physics or deeper principles we have yet to grasp. It stands as one of the greatest unresolved questions in modern theoretical physics. For our journey through the arrow of time, this puzzle is a gentle reminder that time's mysteries are intertwined with the fundamentals of reality. On the one hand, the universe seems to demand that no information ever truly vanishes, a kind of ultimate bookkeeping that, if upheld, means even black holes cannot break the cosmic ledger. On the other hand, black holes present a face of absolute finality and irretrievability, an embodiment of irreversibility at the edge of space and time. However it is resolved, the black hole information paradox will teach us something profound about how time and quantum mechanics mesh together. It shows that even in the quiet depths of theory, the arrow of time raises questions. We find that at the very frontier of physics, we are still asking, can something that has happened ever be completely undone? Or is there always some trace that endures, in the delicate Hawking radiation, or the faint whispers of information at a horizon's edge? Nature may yet reveal an answer. Until then, the paradox stands, a silent marker of how much we still yearn to understand about time's irreversible course. Nearly 14 billion years ago, the universe's first fire was lit, the Big Bang's incandescent explosion of heat and light. In that newborn cosmos, as we've seen, time's arrow began pointing steadfastly forward. from an extraordinarily hot, uniform blaze toward an ever-expanding, ever-cooling future. Over eons, that initial fireball gave way to stars and galaxies, which themselves will eventually fade. We are living in the middle chapters of this great cosmic story, at a time when stars still shine and life can flourish under their warmth. But the trajectory is clear. The cosmos is slowly drifting from that blazing beginning toward a state of embers. One day, trillions of years hence, the universe will likely be a very quiet place. Its once brilliant fires will be gone, leaving only faint whispers of heat remaining in the vast darkness. In that far future, all stars have long since burned out, leaving behind remnants, black dwarfs, neutron stars, and black holes. Galaxies themselves dim as their stars wink out one by one. Even black holes, given enough time, evaporate into faint radiation. The universe's matter will be spread thin, at nearly uniform low temperature. It will be a cosmos of gentle embers, perhaps a thin haze of particles and low-energy photons, a far cry from the brilliant inferno of the beginning. Time will still march on, but in a near-empty, unchanging expanse, the distinction between past and future could blur. With virtually nothing happening, the arrow of time would become nearly irrelevant. It is as if time itself would hold little meaning in such a still cosmos. This is the projected endpoint of the thermodynamic and cosmic journey. Maximum entropy, a kind of cosmic quietus. In essence, the thermodynamic arrow of time, entropy increase, and the cosmic arrow, expansion and cooling, are two sides of the same coin. They both trace back to that low entropy fiery start and proceed toward the high entropy cold end. Every irreversible process that we witness, from ice melting to stars exhausting their fuel, is part of this grand progression. When your coffee cools in the morning, it's ultimately because the universe is expanding and allowing heat to disperse. When eggs scramble and never unscramble, it's because entropy is on this one-way escalator set in motion by the initial conditions of the cosmos. The arrow of time that governs our daily lives is intimately connected to the fate of the universe as a whole. In a world without an arrow of time, cause and effect, memory and progress would all be meaningless. But we live in a universe where the past leaves traces, like fossils, memories, records, and the future remains unwritten. We remember yesterday precisely because entropy was lower then, and our brains can store a record of it, whereas tomorrow's state is still uncertain. The fact that we grow older and not younger, that we recall the past but not the future, is a direct consequence of the thermodynamic arrow. Our human experience of time, with all its nostalgia and anticipation, is deeply rooted in the physics of an evolving universe. As we link the thermodynamic arrow to the cosmic arrow, we come to see them as one and the same grand tale. The universe began in a blaze of low entropy and marches inevitably toward a quiet, high entropy twilight. Every tick of a clock, every irreversible moment in our lives participates in that grand unfolding. We find ourselves in an extraordinary position, creatures of entropy's middle act, witnessing the cosmos in its vibrant youth, yet aware of a distant, quieter future. It is a humbling and profound realization. The arrow of time, stretching from the first fire to the last ember, gives context to our existence and direction to history. And while physics can describe why this arrow exists, there remains a deeply human aspect to its passage, one of memory, experience, and meaning. The story of time's arrow is not just about the universe out there, but also about us, and how we navigate the flow that never reverses. In the end, The forward movement of time defines everything we know, urging the universe, and us along with it, into the ever-unfolding future. The rule-book that governs our universe is based on a lie. Okay, maybe not a lie, but a massive oversimplification. It's a beautiful, elegant rule-book, written in the language of math. Its equations describe the grand dance of galaxies, the buzz of atoms, and the gentle arc of a thrown stone. But here's the catch. The vast majority of these laws of physics, from Newton to Einstein to the weird world of quantum mechanics, don't have a preference for the direction of time. They work just as well forwards as they do backwards. Think about it. A movie of planets orbiting a star would look perfectly normal in reverse. A video of two billiard balls colliding is just as believable played backwards. According to our deepest equations, the past and the future are on equal footing. So why does this never, ever turn into this? Why doesn't a shattered egg magically reassemble itself? Why doesn't a cold cup of coffee spontaneously get hot? Our reality, the world we actually live in, is a stubborn, unbreakable, one-way street. We call it the arrow of time. It seems the universe cheats its own rules. It builds a path from past to future that you can never, ever turn back on. The truth isn't that the laws are wrong, but that we've been missing a huge piece of the story. A story that starts with the state of our universe at the very beginning and finds its how in the strangest corners of reality. A phenomenon we call quantum weirdness. We're going to expose that secret, and in doing so, unravel one of the deepest mysteries in all of science: why time only moves forward. To understand the lie, you first have to appreciate the beautiful symmetry it's built on. Imagine you're watching a video of two billiard balls on a perfect, frictionless table. One is still, the other rolls towards it. They click, collide, and scatter. Now, rewind the video. The two scattered balls roll back, collide, and send the first ball zipping back to where it started, leaving the second one perfectly still. Which video was real? The forward one? Or the reverse one? You can't tell. Both versions are completely plausible. Both obey the fundamental laws of motion Isaac Newton laid down centuries ago. His laws are all about forces, mass, and acceleration. If you take his equations and just swap the variable for time, t, with negative t, they still work perfectly. This property is called time reversal invariance, and it's not just some quirk of Newton's old ideas. Flash forward to the 19th century, to James Clerk Maxwell. He unified electricity and magnetism into a single, stunning theory of electromagnetism. His equations describe light itself, and just like Newton's laws, they're time-symmetric. A light wave travelling away from a source is a perfectly valid solution, but so is a wave converging back to a single point. The laws themselves don't forbid a reverse light bulb that sucks in ambient light. Reality, of course, does. Then came the 20th century, and our understanding of reality was blown up twice. First, by Albert Einstein. His theories of relativity weave space and time into a single fabric, spacetime, and yet again, at their heart, his equations are time-symmetric. A star collapsing to form a black hole is a valid solution, but so is a white hole. A black hole running in reverse, spewing out matter and energy. The second revolution was quantum mechanics. It's famously bizarre, a world of probabilities where particles are also waves. The central rulebook, the Schrödinger equation, describes how a quantum system evolves over time. And for the most part, you find the same old story. As long as a quantum system is perfectly isolated, the Schrödinger equation is time reversible. You can use it to calculate the past, just as easily as you can calculate the future. So here's the paradox, laid bare. The fundamental laws that underpin almost everything have this deep, profound symmetry. They don't distinguish between past and future. They treat time as a two-way street. So why, in our world, does the movie only ever run in one direction? This is the lie. Not a malicious one, but a lie of omission. The laws aren't wrong, but they are clearly incomplete. We don't need a physics lab to see the evidence. It's everywhere. You knock a glass of wine off a table, and it shatters, a red stain spreading across the floor. You have never, not once, seen a puddle of wine and 1,000 shards of glass leap off the floor to reassemble a full glass on the table. You pour milk into your coffee. The two liquids swirl into beautiful patterns before settling into a uniform, light brown blend. You could stir it for 1,000 years, but you'll never see the milk and coffee spontaneously unmix themselves. Everywhere you look, you see processes that only happen one way. Buildings crumble, but don't uncrumble. People grow old, but not young. This one-way street, this obvious difference between past and future, is what the physicist Arthur Eddington famously called the arrow of time. And it's not just one arrow, it's a whole quiver of them, all pointing in the same direction. There's the thermodynamic arrow of time, the one we see in the coffee cup. It's the tendency for things to go from order to disorder. This is the big one, and we'll come back to it. There's the cosmological arrow of time. We live in an expanding universe. Galaxies are flying away from each other. If you run the clock backwards, you see them all rushing together toward the Big Bang. Why expansion and not contraction? That points a direction in time. There's the radiative arrow of time. When you toss a rock into a pond, ripples spread outwards. They never spontaneously emerge from the edge of the pond and converge to shoot a rock into the air. Waves just seem to radiate away from their source. And maybe most personally, there's the psychological arrow of time. We remember the past. We have books, photos, fossils, records of what's already happened. We don't have memories of the future. We can guess, we can predict, but we can't remember tomorrow. All of these arrows point in the same direction, from past to future. The universe ages, it evolves, and it never, ever goes back. So we have a genuine conflict on our hands. A set of fundamental laws that are stubbornly time-symmetric, and a universe that is blatantly, aggressively, time-asymmetric. Something has to bridge that gap. To find it, we have to look at the concept that underlies almost all of these arrows. A strange, often misunderstood, but profoundly important quantity called entropy. If you want to understand the arrow of time, you have to understand entropy. The idea came about in the 19th century from a very practical problem: building better steam engines. Physicists studying heat and energy discovered a new law of nature, the second law of thermodynamics. Put simply, it says that in any isolated system, entropy will either stay the same or increase. It never goes down. So what on earth is entropy? The common definition is that entropy is a measure of disorder or randomness. A tidy room is a low entropy state. Everything is in its ordered place. Left to the chaos of life, it gets messy. The entropy, the disorder, increases. It takes energy and effort to clean the room and lower its entropy. But in doing so, you breathe, you generate heat, and the total entropy of you plus the room still goes up. The second law always wins. But disorder is a bit fuzzy. The physicist Ludwig Boltzmann gave us a more precise definition. He realized that what we see as temperature or pressure are just the average behaviors of a ridiculous number of atoms. For Boltzmann, entropy is a measure of how many microscopic arrangements can produce the exact same macroscopic state. Let's go back to the coffee and milk. When they're separate, there's a relatively small number of ways to arrange the molecules to keep them that way. All the milk molecules have to be on one side, and all the coffee molecules on the other. This is a low entropy, ordered state. Now, let them mix. That uniform, light brown state can be achieved by an astronomically larger number of microscopic arrangements. A milk molecule could be here, or there, or swapped with a coffee molecule, and the drink would look identical. This is a high entropy, disordered state. The second law of thermodynamics, then, isn't some cosmic command. It's just a statement of overwhelming probability. There are just vastly, incomprehensibly more ways to be in a high entropy state than a low entropy one. So, any system will almost certainly evolve toward the state with the most possible arrangements, maximum entropy. An egg breaks because there are countless more ways for its atoms to be arranged as shattered egg than as pristine egg. The reverse is not impossible, just so fantastically improbable that it will never, ever happen. This is the source of the thermodynamic arrow of time. The past is different from the future, because the universe is moving from a state of lower entropy to higher entropy. But this just pushes the question back. If entropy is always increasing, that must mean that in the past, it was lower. Much lower. In fact, if you trace it all the way back 13.8 billion years to the Big Bang, you have to conclude that the universe began in a state of absurdly, mind-bogglingly low entropy. This is the past hypothesis. The early universe was an incredibly hot, dense, uniform plasma. That sounds pretty disordered, right? But here's the twist. Gravity flips the script. In a universe with gravity, a smooth, uniform soup is actually a very low entropy state. Gravity wants to pull things together. Over time, it turns that smooth gas into a lumpy universe full of stars and galaxies. The high entropy state for our universe is one full of black holes. So, the initial smoothness of the Big Bang was a state of profound order. Why? Why did our universe start in this 1 in a trillion low entropy state? We don't have a final answer. But we know that this special starting point is the ultimate reason we have an arrow of time. The universe was wound up like a cosmic clock at the beginning, and it's been unwinding ever since. But how exactly do time-symmetric laws produce this irreversible unwinding? For that, we need to dive into the quantum realm. Entropy tells us that the arrow of time is a statistical game, born from the universe's highly improbable starting line. But that feels incomplete. The rules for individual particles are time-symmetric. How does the irreversible behavior of the crowd emerge from the reversible behavior of the individuals? A newer, deeper explanation is taking shape, and it suggests the arrow of time is baked into the very fabric of quantum reality. The true enforcer of time's one-way street isn't just probability. It's a pair of famously weird quantum phenomena: decoherence and entanglement. Let's start with decoherence. In the quantum world, a particle can be in a superposition of many states at once. An electron isn't spinning clockwise or counterclockwise. Until you measure it, it's in a probabilistic blend of both. This is called coherence. A perfectly isolated quantum system would happily follow the time-reversible Schrödinger equation forever. But here's the catch. It's basically impossible to perfectly isolate anything. Your cup of coffee is constantly interacting with the air molecules around it, the light hitting it, the table it's sitting on. Every quantum system is unavoidably connected to its environment. When a quantum system in a superposition interacts with its environment, information about its state leaks out and spreads into the trillions of particles outside. This leakage of quantum coherence into the environment is called decoherence. The superposition is gone, not because it was magically destroyed, but because it has been smeared out across an impossibly vast environment. To reverse this, to recohere the system, you would have to track down every single particle that interacted with it and perfectly reverse its trajectory. That's not just improbable, it's practically impossible. Decoherence is a one-way street. It explains why we see definite outcomes in the world, and it imposes a direction on time at a very fundamental level. Now, let's bring in its partner in crime, quantum entanglement. This is what Einstein famously called spooky action at a distance. When two particles become entangled, they share a single quantum state. No matter how far apart they are, measuring one instantaneously influences the other. They are two parts of a single whole. Just as a system inevitably interacts with its environment, it also inevitably becomes entangled with it. Every interaction creates new threads of entanglement. The universe is a vast, ever-growing web of these quantum connections. This process creates a record. The state of the universe now contains the imprints of past interactions, stored in this intricate network of entanglement. The present is correlated with the past in a way it isn't with the future. This has led some physicists to propose a quantum version of the past hypothesis. The idea is that at the Big Bang, the universe began not just with low thermodynamic entropy, but also with extremely low entanglement. It might have been a simple, unentangled state. Since then, as particles have interacted, the total amount of entanglement has been constantly and irreversibly increasing. This growth of entanglement is, itself, a fundamental arrow of time. Okay, let's put all the pieces together. We started with a paradox: the reversible rules of physics versus our irreversible reality. The first piece of the puzzle was the second law of thermodynamics. It tells us that the universe moves from order to disorder, from low entropy to high entropy. This is a statistical certainty. Systems just evolve towards their most probable state. This gave us the thermodynamic arrow of time. But that led to the past hypothesis. For entropy to be increasing now, it must have started at an absurdly low point. The universe's initial condition at the Big Bang was incredibly special and ordered. This is the ultimate anchor for time's arrow. The laws are symmetric, but the starting point was not. But that still didn't explain the how. How did time-reversible microphysics produce irreversible macro behavior? That's where the quantum conspiracy provides the mechanism. The constant interaction between any system and its environment causes two things. 1. Decoherence. Quantum possibilities leak into the environment, making the process practically irreversible. It's what makes our world look solid and definite. 2. Entanglement. With every interaction, the web of quantum correlations grows, creating a physical record of the past within the present state of the universe. So now we have the complete picture. The lie wasn't in the laws themselves. Most of them are time-symmetric. The real story is a two-parter. Part 1 is the initial condition. The universe began in a highly specific, low entropy, and likely unentangled state. Part 2 is the mechanism. Quantum decoherence and the spread of entanglement are the physical processes that enforce the second law. They take time-symmetric quantum rules and produce outcomes that are, for all practical purposes, irreversible. The thermodynamic arrow and the quantum arrow are two sides of the same coin. The increase in entropy is the macroscopic shadow of the microscopic spreading of entanglement. The universe isn't just getting messier, it's getting more correlated, its history etched more deeply into its quantum fabric. Explaining these deep concepts is what we love to do. If you enjoy untangling the biggest mysteries of the universe, from the nature of time to the secrets of black holes, consider subscribing and hitting that notification bell. It really helps us continue to explore the frontiers of science. And for those who want to support us more directly, you can check out our Patreon page. So, is the mystery solved? In many ways, yes. We have a compelling story connecting the Big Bang to your morning coffee. The lie of time reversibility was a clue, pointing toward the universe's unique history and its deep quantum nature. But what about that little exception I mentioned at the start? It's true that there are rare interactions involving the weak nuclear force, where time symmetry is genuinely broken at a fundamental level. While these violations are crucial for understanding other cosmic mysteries, like why there's more matter than antimatter, they are tiny effects. They don't explain why a wine glass shatters. That's a story of entropy and quantum mechanics. The biggest remaining question mark hangs over the very beginning. Why? The past hypothesis. Why did the universe start in such a special, low entropy state? Was it a random fluctuation? A feature of a multiverse? We just don't know. That is the next frontier. What we do know is that the arrow of time is not an illusion. It emerges from the peculiar starting conditions of our cosmos and is driven by the fundamental weirdness of quantum mechanics. Every moment that passes, the universe becomes a little more entangled, its story a little more complex. The lie of reversible time has led us to a profound truth. The universe is a recording device, and the very act of recording is what pushes time forward. And as we look out into the cosmos, we aren't just seeing space. We are looking at a 13.8 billion-year-old story, written into the quantum state of the universe. A story whose next chapter is, and always will be, unwritten. All around us, events unfold in an irreversible procession. A teacup shatters on the floor and remains broken. Smoke from a candle disperses into still air and does not gather back into flame. Yet deep in the laws of nature, there is no rule that says these processes must only go one way. The fundamental equations, the rules that govern how each particle moves or each wave spreads, work perfectly well forward or backward in time. In principle, if every molecule's motion in that puff of smoke were exactly reversed, the smoke would curl itself back into a plume and slip neatly into the candle. But in all the days we have watched candles and smoke, we have never seen such a reversal. The equations may be reversible, but the story they write is not. It is a gentle paradox, the difference between the reversible language of the microscopic world and the irreversible drama of the macroscopic world. Imagine observing a single collision between two atoms. If you filmed that tiny event and played it backwards, it would look entirely plausible. One atom leaves, two approach and collide, then separate. Nothing about that reversed film would violate the microscopic laws. But if you film a large scene, say a glass falling off a table and smashing, and run that backwards, it looks absurd. The shards do not spontaneously leap up to reassemble the glass. Spilled water does not collect itself back into the cup. Somewhere between the simple atomic collision and the shattered glass, an arrow of time has emerged. Physicists long pondered how such an arrow could appear. In the late 19th century, as the understanding of atoms and energy began to take shape, a physicist named Ludwig Boltzmann proposed a bold idea. He suggested that the arrow of time The tendency for things to move from order to disorder is not a fundamental commandment of physics, but a matter of statistics. Picture a neat arrangement of playing cards that accidentally falls to the floor. There are vastly more jumbled card arrangements than neatly stacked ones. So after a fall, you almost always find a messy scatter of cards, not an intact deck. Boltzmann argued that just like the deck of cards, nature favors the overwhelming multitude of disordered states over the rare ordered ones. This explains why entropy, the measure of disorder, tends to increase. But even Boltzmann's persuasive idea left a puzzle. If the basic laws allow order to increase or decrease equally, what ensures that we started in a relatively ordered state to begin with? A friend and critic of Boltzmann, Joseph Loschmidt, voiced this very concern. If every microscopic interaction is reversible, how does the universe know to head towards disorder rather than away from it? In other words, what picks the direction of time's arrow? The resolution, subtle yet profound, lies in initial conditions. The universe, for reasons still not fully understood, began in a state of extraordinarily low entropy, a very special, highly ordered arrangement. It's like beginning a story with a pristine library where all the books are neatly shelved. As the story unfolds, books are taken out and left on tables, pages get shuffled, the order degrades. The physics doesn't force the mess to grow, it simply doesn't prevent it. If the library had started in chaos, one could in principle find rare moments where a bit of order increases, but that's not our situation. We started in order, so the natural trajectory is towards disorder. From tiny quantum seeds, classical fields of reality grow, guided by these conditions. Imagine the early universe as a field of energy, smooth and uniform, but with minuscule quantum fluctuations. Little random differences, here slightly denser, there slightly thinner. These quantum seeds are inherently unpredictable, but once planted, they were stretched and amplified as the universe expanded. Over billions of years, those tiny initial imbalances gave rise to galaxies and clusters of galaxies, the grand structures we see in the sky. In this way, a fundamentally reversible equation describing a quantum field could still give rise to an irreversible cosmic history. The quantum seeds could have in principle yielded countless different cosmic arrangements, but we experience only one realization, the one that actually unfolded. Once it unfolded, there was no turning back the cosmic clock to try a different outcome. The universe's expansion and cooling are one-way events. The gravity that pulled matter into galaxies doesn't spontaneously reverse to fling it all apart evenly again. We see a similar principle in the everyday world. The slightest unpredictable nudge at the microscopic level can send events cascading in one irreversible direction. Think of a ball balanced on a hilltop. A breath of wind, or even a thermal jostle of air molecules might tip it to one side. Down it rolls, gaining speed, and perhaps knocks over a row of dominoes at the hill's bottom. If you attempted to reverse this sequence, you'd have to get every domino to stand itself back up and the ball to roll precisely back up the hill to its peak. Even if the laws allow such a reversed path, executing it requires an exquisitely choreographed conspiracy of countless particles and forces. In practice, the world does not perform that kind of miracle. The microscopic equations remain reversible, but once many pieces are involved, the chance that all reverse together in perfect sync is effectively zero. Instead, one tiny cause leads to a chain of effects. The ball's fall leads to toppled dominoes, and those effects branch out and entangle with the world around them. In this way, reversible equations give rise to irreversible stories. The arrow of time emerges quietly from a confluence of factors: the special low-entropy beginning of the world, the immense odds favouring disorder, and the amplification of small uncertainties into large outcomes. Each event leaves a mark, a footprint on reality's canvas, and those marks accumulate rather than erase. A spilled glass leaves shards and a puddle. Cleaning it up still involves work and increases entropy somewhere else. The story moves forward, each chapter built upon the last. The past is written down in these remnants, while the future remains open and undefined. In the interplay between quantum seeds and classical fields of events, the narrative of time is continually being written in one direction. The fundamental rules might not dictate an irreversible narrative, but once the narrative starts writing itself from that low entropy introduction, the plot naturally thickens in the forward direction. At the tiniest scales of nature, another subtle arrow of time reveals itself. In the quantum realm, particles can exist in a ghostly blend of possibilities, what we call a superposition. A single electron can be in two places at once, or a cat, in Schrödinger's famous thought experiment, can be both alive and dead in a suspended limbo. Yet whenever we check, whenever we perform a measurement, we always find a single, definite result. The electron here or there, the cat either alive or deceased, never both. The question is, how do these crisp outcomes emerge from the haze of quantum possibility? What breaks the symmetry of all those might-bes and chooses the is that we actually see? The answer comes in a soft whisper, not a loud command. It's called decoherence, and it is like the gentle murmur of the environment that is always listening. Imagine that our quantum particle, say, that wandering electron, isn't truly alone. Even in an isolated lab chamber, there are stray atoms in the air, faint electromagnetic fields, perhaps a bit of warmth in the apparatus. These surroundings constantly bump into, interact with, and observe the particle in countless tiny ways. Each interaction is like a little measurement. A single photon bouncing off the electron can carry away a clue about the electron's position. One by one, these subtle whispers from the environment extract information about the particle's state. As the environment listens in, something profound happens to the quantum system. The many possible states that the particle could be in, here, there, everywhere, start to lose their ability to interfere with one another. It's as if the particle's multiple possibilities were like delicate musical notes ringing in unison. Decoherence is the process by which noise from the environment dampens and silences all but one note. The quantum superposition isn't outright destroyed, but it becomes effectively hidden, shuffled away into correlations with the environment. To any observer who isn't tracking every last air molecule and photon, the particle now appears to have chosen a definite state. This process requires no conscious observer, no deliberate act. It happens naturally and incessantly. The world around any quantum object essentially measures it all the time, but quietly. We call it a measurement when we humans finally take note, but by then, the environment has often already done the job. Picture opening Schrödinger's box. Before you peek in, the cat inside has been interacting with air molecules, perhaps meowing or moving. Those interactions have long revealed the cat's condition to the environment inside the box. When you finally lift the lid, you're just getting the news that the box's interior had already broadcast in tiny, irretrievable signals. The outcome, alive or dead, appears definite by the time you look, because countless particles in the environment have already locked in one possibility. Once decoherence has happened, the different possible outcomes can no longer interfere or mesh together. In principle, quantum mechanics hasn't abolished the other possibilities entirely. They're still present in the grand quantum state of the universe, entangled with different states of the environment. But for all practical purposes, Each alternative might as well be in a separate world, unable to affect the one we experience. In our world, we see one outcome, consistent and solid. The egg is broken and remains broken. The particle hit the detector on the left and nowhere else. The alternatives are now out of reach, encoded in subtle correlations that would be nearly impossible to ever collect and reverse. This irreversibility of measurement gives the quantum arrow of time a character similar to the classical one. Before a measurement, a system's evolution can be mathematically run backwards or forwards with equal ease. The equations permit time symmetry. But after decoherence, after a measurement outcome has become known, there is an effective increase in the disorder or entropy. Information that was once neatly confined within the system's wave function has leaked into the environment, like dye spreading through water. To reverse the measurement, one would have to gather all those dye molecules, all those entangled bits of environment, and restore them to their original state. In practice, that is no more feasible than unbreaking a glass or unstirring cream from coffee. Yet, nothing mystical is needed to explain this. We do not require a special collapse postulate or a dramatic intervention to make the outcome definite. The gentle, continuous murmur of decoherence is enough. It explains why we perceive a concrete reality instead of a blur of maybes. The equations of quantum physics still hum along, reversible under the covers. But decoherence hides their time symmetry behind a statistical veil. The arrow of time sneaks into quantum measurements, not because the fundamental laws strictly force a direction, but because the act of information dispersal, the environment's eavesdropping, cannot be undone. Much like a secret whispered to a crowd, the quantum secret, once out, cannot be put back in its box. And so, when we observe the world, we find it in a definite state, a clean story that moves forward from one measurement to the next, gently but firmly steering quantum possibilities into the single reality we know. Every event that unfolds in our world leaves behind a web of connections. When a quantum measurement occurs, for example, the system and the environment become linked in a precise way. They are said to be entangled, bound by the outcome that was selected. Entanglement is an intimate union. When two things are entangled, neither can be fully described without the other. It's as if the fate of each is tied together by invisible threads. After a measurement, the particle carries one piece of the story and the environment carries another. The result is written into the fabric of the world as a correlation between them. In this way, a simple event, a particle hitting a detector, a droplet of wine staining a tablecloth, doesn't just happen and vanish. It leaves traces, records of itself, woven into the world. These records are remarkably persistent. Once information from an event spreads into the environment, it becomes extraordinarily difficult to erase. Imagine a single flash of light in a dark forest at night. For an instant, the trees and the ground are illuminated. In that moment, countless leaves and rocks have absorbed or reflected the light. They now carry a tiny imprint of that flash, perhaps a warmed patch or a photon scattered off. The flash may be gone, but its effects have scattered in all directions. To undo the flash, you would have to somehow recapture every photon that escaped and cool every warmed leaf back to its exact previous state. Practically speaking, that's impossible. The forest has recorded the flash, and there is no realistic way to expunge that memory. In our everyday experience, the idea is the same. A cup that falls and breaks imprints its story on the world around it. The sound waves from the shatter travel through the air and slightly vibrate the walls. Bits of glass scratch the floor. Dust is displaced. Anyone nearby who saw or heard it now carries a memory of the broken cup. These are all records, large and small. They are the physical echoes of what happened. Importantly, they stick around. The air doesn't unvibrate and give back the sound. The floor doesn't unscratch itself to erase the evidence. Your mind doesn't spontaneously forget the event at the same time in reverse. Instead, all these traces collectively serve as proof. The cup was intact in the past, and then it broke. Entanglement ties together all the pieces involved in an event like this. On a quantum level, the molecules of the cup become entangled with the molecules of the floor, the air, even the photons of light that scattered from the breaking. This entanglement means that, in the grand quantum description, the state of the cup is now inseparable from the state of its surroundings. If you somehow had godlike knowledge of every particle's quantum state after the cup shattered, you could in principle infer that a break occurred. But only under fantastically controlled conditions could one even imagine nudging all those particles to reverse their course and undo the break. In the real world, each particle goes its way, carrying a bit of the story. The entanglement fan-out, from cup to air to room to earth and beyond, ensures that the arrow of that event points forward. The broken cup's influence has permeated its environment, and there is no easy way to gather all those influences back again. Over time, more and more such correlations build up. The present moment holds a vast collection of records of the past. We see them in history books and fossils underground, in the lingering warmth of the ground after the day's sun. Even distant starlight is a record of events eons ago, still travelling through space. But we find no comparable records of the future. Nowhere in the present will you find a footprint from a walk you haven't taken yet, or a page in a diary filled in with next year's events. The asymmetry between past and future, in terms of records, is striking. It's precisely because entanglement and the diffusion of information work only one way. The universe keeps an account of what has happened, but it does not seem to pre-write what will happen. This one-way recording of reality is deeply connected to the arrow of time. At root, the arrow emerges from the fact that you can't put the genie back in the bottle. Once information is let loose into the environment, the correlations that form are effectively permanent. They might diffuse further, becoming diluted and harder to read, but they won't spontaneously funnel back and disappear. Think of a drop of ink spreading in water. The intricate swirls are the record of the drop's release. Given infinite care, one might attempt to corral the water and ink back to its initial state, but any misstep and it still spreads again. Nature doesn't do this reversal on its own. Instead, each interaction, each entangling of one thing with another, adds to the growing record of time's passage. Thus, entanglement and its resulting records give the arrow of time a cumulative character. The world is constantly writing its history in the form of these interconnections. And because those connections persist, we experience a sense of progression. We remember the past, for it's inscribed everywhere, including within our brains. And we anticipate the future, which has yet to be inscribed. The ties that bind events and their records ensure that causes remain in the past and cannot suddenly spring from the future. In the entangled tapestry of reality, each thread runs only one way. The past and the present are woven together, and from that fabric the future will emerge, unweaving nothing but weaving anew as time flows forward. If every rule can be broken by a fluke, one might wonder, could time's arrow itself ever flip, even briefly? After all, the laws of physics do allow, in principle, for strange coincidences. A shattered egg could, in theory, have all its pieces jostle in just the right way to leap up and assemble again. The air in your room could by random chance collect itself into one corner, leaving you gasping in vacuum. These things are so immensely unlikely that we'd never expect to see them in the age of the universe. But more importantly, even if such a bizarre event occurred, it would be a local hiccup, not a rewind of the entire world. In reality, rare backward blips do not create a sustained reverse story. They are fluctuations, not films. Consider stirring milk into coffee. As you stir, white tendrils of milk snake through the dark coffee, eventually blending into a light brown mix. There is an astronomically small chance that, if you waited long enough, the random motions of molecules could produce a momentary unmixing. A little white swirl might briefly reform amidst the brown. But you'd likely never catch it. It would be fleeting and soon washed away by more mixing. And crucially, the coffee cup on the table won't freeze in time or grow younger to match that tiny swirl. The overall process stays moving forward. One brief decrease in entropy doesn't set the entire arrow of time pointing backward. This points to a key distinction. Small-scale reversals can happen in isolated pockets, but they do not propagate and amplify. Imagine a chilly morning where you can see your breath. You exhale a warm cloud of vapor that soon dissipates. In principle, a stray gust of wind and fluctuations could momentarily gather some of that vapor back into a faint cloud, as if part of your breath unexhaled itself. But the moment passes, and the cloud scatters again. The world at large didn't run in reverse. Your breath didn't flow back into your lungs, and time didn't truly rewind. It was just a tiny eddy in the ever-forward stream. In physics terms, what we call a fluctuation might slightly decrease entropy in one spot for a short time. Given an incredibly vast number of particles jiggling about, occasionally a few might by chance all head in a coordinating direction that creates a pocket of order. But the odds of a large, sustained decrease in entropy, enough to resemble a reversed sequence of events, are so overwhelmingly low that for all practical purposes, they can be treated as zero. The universe is not finely tuned to produce conspiracies of chance that undo macroscopic events. Instead, it relentlessly explores the vastly more numerous ways to increase disorder. The idea of extreme fluctuations leads to whimsical musings. One could imagine, in an unimaginably far future, a disordered gas randomly fluctuating into a brief imitation of a living being or a memory of the past. But these fantasies underscore the point. A fluctuation capable of recreating something as structured as our present world is absurdly more improbable than simpler paths. Our arrow of time is not at the mercy of such freak occurrences. If anything, the fact that we even consider these scenarios highlights how firmly one way our everyday reality is. We have to stretch our imaginations to their limits to picture time even hinting at running backward. Even in the realm of quantum physics, where randomness is intrinsic, time's preferred direction holds steady in practice. A particle might momentarily do something unexpected, like move against a gradient, but the surrounding environment quickly absorbs the anomaly. There's no chain reaction that makes the entire laboratory run backward. The forward march of statistical tendencies swamps any single quirky step. In essence, the arrow of time is a robust, emergent property. It's not easily perturbed by 1 in a trillion chance events, much as a mighty river isn't sent flowing backwards by a tiny ripple against the current. So, while physics doesn't forbid a backwards blip here or there, it does not allow those blips to blossom into a reversed world. What we see instead is stability. Broken eggs stay broken. Smoke doesn't return to candles. and coffee stays mixed. On rare occasions, a small fluctuation might mimic a piece of the reverse process. But it's a fragmented illusion, not a true rewind. Time's arrow, forged by the collective behavior of countless particles and the special conditions of our universe, remains unbroken by these minor caprices. In the grand narrative, the odd backward moment is just that, a momentary whisper in an ongoing symphony that overwhelmingly plays in one direction. Physics, at its most fundamental level, doesn't prefer one direction of time over the other. If you were to write down Newton's laws of motion or the equations for particle collisions, you'd find they work just as well, run in reverse. A video of ideal billiard balls colliding on a frictionless table looks equally valid, whether you play it forward or backward. The same is true for electromagnetism and even quantum theory's basic equations, as long as you don't include the act of measurement. There is a deep symmetry in the core laws. They don't come with an arrow stamped on them saying future or past. And yet, the world we experience is full of processes that go one way and not the other. How can both be true? The resolution lies in the conditions, not the commands. The laws of physics are like rules of a game that allow many outcomes, but the starting setup of the game determines how it will play out. Our universe's starting setup, the initial conditions at the Big Bang, was highly ordered, like a freshly reset chessboard or an immaculate house before a party. From that special beginning, entropy had essentially one way to go: up. The equations didn't mandate increase entropy now. They simply permitted it, and given the starting state, increasing disorder was overwhelmingly likely. If the universe had begun in complete chaos, with maximum entropy, we would not have a built-in arrow of time. Everything would already be in a dull, equilibrium haze, with no memory of a more ordered past. But we live in the wake of a very low entropy dawn. All arrows point away from that dawn, simply because there's no plausible path to go further into order. The only natural path is towards disorder. Imagine watching a film of an egg splattering on the floor. The fundamental forces governing each piece of shell and each drop of yolk are time-symmetric. If you reversed the velocities of every particle at the moment after impact, all the pieces would fly back together and the egg would reassemble, perfectly consistent with Newton's laws. Yet such a reversal requires an almost impossibly precise coordination, a very special arrangement. In our actual world, no invisible hand is setting all those particles on exactly the right paths to make the egg jump off the floor. Instead, all those particles were set on a collision course when the egg was still intact and held up high. The asymmetry comes from how things started and how they were arranged, not from the fundamental forces themselves yelling, "Go that way." This insight was one of Boltzmann's great contributions, that the arrow of time comes from improbable beginnings. It's not that entropy cannot decrease. It can, under the laws, if ever circumstances arrange themselves just right. It's that our world was never arranged in that special way to make entropy decrease on its own beyond tiny fluctuations. The past-future divide is not written into the equations of motion, but into the boundary conditions of the universe. The early cosmos set the stage by being so low entropy that everything since has been a journey toward higher entropy. In everyday terms, the difference between yesterday and tomorrow isn't because physics changes its mind overnight. It's because yesterday's state was different from what tomorrow's will be. This perspective also tells us why we can't simply undo the arrow by fiddling with the laws. There's nothing lopsided in the equations to fix. Instead, the asymmetry is in the initial state. It's akin to winding up a clock. The clock's mechanisms, the laws, allow motion either way, but you wound it in a particular way and released it, so it ticked forward. Similarly, the universe was somehow wound into a low entropy configuration and then released, and it's been unwinding ever since. Scientists still ponder why the Big Bang had such an extraordinarily ordered beginning. That remains a deep puzzle. But given that it did, all the irreversible phenomena we see are natural consequences. In short, time symmetry survives in the fundamental equations, but the clear division between past and future comes from those one-time cosmic conditions. Our universe follows time-symmetric rules, set in motion from an initial condition that breaks that symmetry in practice, giving rise to the one-way flow we observe. Amid the near-perfect symmetry of nature's laws, there lurk a few subtle asymmetries. For decades, physicists assumed that the fundamental equations were completely time-symmetric, but in the mid-20th century, experiments with tiny unstable particles revealed a surprise. Some processes have a slight built-in preference for one direction in time. This was first noticed in the decay of certain particles called kaons. The decay products didn't behave exactly the same when the process was watched in a time-reversed mirror world. In technical terms, they violated a symmetry called CP, which, by a deep linkage in physics, implies a violation of time reversal symmetry as well. In other words, the universe at a microscopic level has a tiny wrinkle that differentiates past from future. Before thinking, this turns our understanding upside down. It's important to emphasize how small and specialized this effect is. These CP-violating processes are rare and occur in the realm of high-energy particles. They don't make eggs unbreak or coffee unmix. In fact, if you were not a particle physicist probing the innards of subatomic decays, you'd never notice this symmetry violation in daily life. The equations of electricity, magnetism, gravity, and the strong force, everything that governs the physics of ordinary objects, remain completely symmetric in time. The slight bias in certain nuclear decays doesn't propagate upward to suddenly make heat flow from a cold stove to a hot kettle or cause smoke to funnel back into a candle. Those everyday phenomena march to the drum of thermodynamics and initial conditions, utterly unbothered by a quirk in particle physics. One significant reason nature bothers with a time asymmetry at all has to do with the existence of matter itself. The tiny preference discovered in particle decays may have tipped the cosmic balance just enough to leave us with more matter than antimatter after the Big Bang. Without it, the matter and antimatter created in the early universe might have annihilated each other entirely, leaving nothing but light. So these minuscule violations might be the reason anything solid exists at all. In that cosmic context, they had a profound effect, a slight skew that meant matter won out by a hair. But once that deed was done, once our universe became filled with matter, the ongoing arrow of time that we experience day to day owes almost nothing to these particle-level imbalances. From the perspective of your kitchen, or your bedroom, or the park outside, the world behaves as if the fundamental laws are perfectly time-symmetric. Apples fall from trees, cups of tea cool, and people age in exactly the way they would in a hypothetical universe where those weird particle decays had no bias. The grand increase of entropy, the flow from ordered to disordered, dwarfs any tiny tilt coming from particle physics. You could say that at the human scale, time's arrow is in a state of big calm. It remains unshaken by the small inner asymmetries of the physical laws. Nature's slight bookkeeping favor for one direction in exotic reactions doesn't translate into a reversal. It doesn't even cause a noticeable hesitation in the everyday arrow of time. It's a bit like a slight imperfection in a clock's gears. That tiny flaw is utterly lost in the steady turning of the clock's hands. The clock of time still ticks forward reliably for us. Its tiny internal biases are hidden deep in the machinery, too gentle to disturb the cadence of the hours. Every living thing is a child of time's arrow. Life depends on time's one-way flow at every moment. Consider how you eat food and breathe oxygen, taking in highly organized energy. Your cells use that energy to build and repair your tissues and to fuel your heartbeat and thoughts. In the process, you break down food and exhale carbon dioxide while releasing waste heat. In essence, you import low entropy order and export higher entropy disorder. This exchange keeps you alive only because there is a gradient between what comes in and what goes out. If the world were perfectly balanced and static, with no gradient of energy to feed on, metabolism would grind to a halt. Life's engine runs on one-way flows, from usable energy to spent energy, from organized nutrients to dispersed waste. From the smallest bacterium to the largest oak tree, metabolism follows this template. Plants capture sunlight, a stream of low-entropy photons from the sun, and use that influx to build sugars and tissues, all the while radiating heat away to cold space. That sunlight comes in one direction, and the waste heat leaves in another. If somehow the sun's light were not streaming steadily forward in time, or if Earth were in thermal equilibrium with no flows, plants couldn't grow. Similarly, animals live by eating plants, tapping the chemical energy that was stored from that sunlight. They then breathe out and excrete the degraded remains. In each case, a living organism sustains its internal order by relentlessly pumping disorder out into its surroundings. Growth, development, and decay are all arrow-bound processes. An acorn sprouts and gradually becomes a towering oak. These changes all require directed flows of energy and nutrients, from mother's milk to the kitten's cells, from soil and sun to the growing tree. We never see an old tree shrink back into a sapling, sucking carbon dioxide out of the air to reassemble a seed, because such reverse growth would violate everything we know about biology and thermodynamics. Likewise, our bodies age and accumulate wear. Cells divide and sometimes make errors, damage accrues. We can slow these processes with care and medicine, but we cannot reverse them. Living things move through time along the gradient of youth to age, and eventually to death and decay, always dissipating energy along the way. Even the concept of life's cycle, birth, growth, reproduction, death, is fundamentally a one-way journey. Life propagates forward in time through offspring. No butterfly returns to its cocoon to unravel its wings. Memory and learning in advanced animals, too, rely on irreversibility. Our brains encode experiences by physically changing, forming new connections or strengthening synapses. We remember the past because our neural circuits have recorded it, but we cannot remember the future in the same way. The arrow of time gives us a direction in which to accumulate knowledge, to evolve, and to experience change. In a very real sense, life is a pattern that only persists by riding the wave of increasing entropy, like a surfer on a crest that forever moves forward. If time's arrow somehow flipped, if entropy flowed backward around us, life as we know it would cease to function. Imagine trying to digest a meal that unchews itself and grows colder in your stomach, wounds that unheal, a heart that unfills its chambers with each beat. These scenarios are absurd because they defy the gradients that make life possible. Fortunately for us, the arrow has never been observed to flip. The universe provides a continuous supply of usable energy, from the sun, from the food we eat, and a sink for waste. In that stable imbalance, life finds room to thrive. We build up pockets of order for a while, bodies, nests, ecosystems, while inevitably contributing to the overall rise of disorder. Far from defying the second law of thermodynamics, life exemplifies it in action. A local bloom of complexity that can blossom only in the presence of a one-way current of energy. We live, in short, in the flow, and if that flow were ever to stop or reverse, so would the fragile processes that sustain our living world. We humans live our lives knowing that what's done is done. There is no rewind button to undo a choice or relive a moment. At first glance, this one-way march might seem to make life more perilous. Mistakes cannot be erased, losses cannot be reversed. But it is exactly this irrevocability that gives our actions weight and our moments meaning. Each decision we make, each experience we have, is unique in time. We treasure a beautiful sunset or a heartfelt conversation precisely because we know it will not come again in the same way. The forward flow of time is what makes each instant precious. In a universe where time only drafts forward, meaning arises from the very fact that we must choose and act without ever truly knowing the final draft of our story. Our sense of purpose is intimately tied to time's arrow. We set goals and work toward them, always oriented toward the future. A painter adds brushstrokes to a canvas, unable to remove those already laid except by painting over. Much as life lets us layer new actions, but not erase the old ones. Knowing that today's brushstroke becomes a permanent part of our life's artwork, we strive to make it count. Reflecting on our past, we see a sequence of events leading to where we are. We cannot change them, but we can learn from them. That learning becomes part of us, guiding our future choices. In this way, the arrow of time grants us agency. It presents us with an unfolding canvas where we can apply what we've learned and attempt new directions, but only going forward. Agency itself, the ability to make choices, would have little meaning in a world where outcomes could simply be reset or reversed at will. It is the permanence of consequences that gives choice its gravity. Because time flows one way, we feel urgency to do what matters now, to apologize while we still can, to try while we have the chance. Our lives gain a narrative structure thanks to time's arrow, a beginning, a middle, and an end that we shape by our actions. All stories derive their meaning from progression. A tale with all the pages jumbled or endlessly rewritten loses coherence. In the same way, our forward-moving lives get their coherence and direction from the fact that they proceed step by step, never backward. There is comfort to be found in embracing this reality. By embracing this reality, instead of longing for an impossible rewind, we recognize that endings and bygones carve out the shape of our existence. Just as the irreversible passing of time gives sorrow its poignancy, it also gives joy its sweetness. A child grows up, and we cherish their childhood all the more because we know it's fleeting. We find meaning in creating memories, in leaving legacies, in affecting others. All acts that presume time will carry on beyond us. Even our idea of hope is rooted in the arrow, the belief that no matter how dark the night, the dawn will come in the future and bring new possibilities. Purpose, in the end, is about moving forward, aiming for outcomes, building relationships, fostering creativity, all things that unfold over time in one direction. Our universe may not allow us to go back and edit our past, but it does allow us to continually write the next chapter. We do so with the understanding that each chapter rests on those before. The mistakes, the triumphs, the heartbreaks and healings, they cannot be undone, but they give context and meaning to what comes next. In this forward-only journey, we find not despair, but inspiration. Knowing that we cannot rewind makes it all the more important to live fully and compassionately in the present, and to envision futures worth striving for. Time's one-way flow is the canvas on which we paint our lives, and within its constraints, we discover freedom. The freedom to create, to improve, to find meaning in the story that moves ever onward.